Welcome, curious reader, to the most useless guide from a practical standpoint that you've ever held in your hands, or flipped through on a screen. Useless because none of the routes described here are ones you will experience. Each of the 13 worlds gathered in this book is a masterpiece in its own right, a masterpiece of hostility, chemical aggression, gravitational violence, or simply quiet, methodical annihilation of all life. The universe, as it turns out, is not particularly interested in hosting guests. It tolerates us only on the tiny blue dot that we arrogantly call home. Step a little further, and it promptly makes clear what it thinks of our arrogance. If you enjoy movies about space, Interstellar, Prometheus, Event Horizon, you already know, the directors did not exaggerate. They perhaps even softened the blow. This book does not soften anything. 13 stories, 13 worlds. Not a single happy ending. If you reach the final page and feel an overwhelming desire to stay on Earth, then we have succeeded. Please like and comment. Which world do you find the creepiest? Let's begin. Story 1. Venus, Hell Wrapped in Pearls. Imagine a sunrise. Not the gray, dreary dawn of a November morning that makes you regret waking up at all. No, imagine a biblical sunrise. The kind from a Renaissance painting, when the sky shimmers in orange and gold, when the horizon burns as if the sun itself has decided to put on a farewell concert before sinking below the horizon. That is the kind of sunrise you will see as you approach Venus aboard a hypothetical interplanetary ship. Through the viewport, the planet would appear as a pearl, tightly wrapped in layers of clouds, colored like melted butter and old ivory. It would glow softly and almost solemnly. The albedo of Venus, that is, its ability to reflect sunlight, is about 70%, making it the brightest object in the night sky after the moon. Our ancestors called it the morning star and the evening star, dedicating goddesses of love and beauty to it. The Sumerians knew it as Inanna. The Greeks called it Aphrodite. The Romans knew it as Venus, a beautiful name for a beautiful planet. This, of course, is a trap. Venus is our closest planet and, by all accounts, the most consistently hostile to all living things among the bodies of the solar system. It is older than most of our notions of what a earthly world should be. It formed about 4.5 billion years ago from the same protoplanetary disk as our Earth, and in its youth, it was possibly much more hospitable. Some planetary scientists seriously consider a scenario where early Venus possessed liquid water and a temperate climate for several billion years. If this is true, it means that somewhere between 2 and 3 billion years ago, Venus made a choice to become what it is today. And this decision was final. The atmosphere of Venus is where any conversation about the planet begins, and, inevitably, where it ends, because the atmosphere is the main killer. It consists of approximately 96% carbon dioxide with molecular nitrogen added in and, as an exquisite garnish, sulfuric acid, forming thick layers of clouds located at altitudes between 45 and 70 kilometers above the surface. It is these clouds that give the planet its pearlescent, mesmerizing appearance. They misled astronomers of the past, who fantasized about tropical jungles and warm seas beneath the opaque veil of Venus, until the mid-20th century, when radio telescopes finally pierced through the clouds and reported something completely unexpected. The surface of the planet is heated to 465 degrees Celsius. Not on the hottest days, not in the equatorial regions, constantly, everywhere. At night, the same temperature as during the day. At the poles, the same as at the equator. The greenhouse effect on Venus has reached what scientists call a runaway state, where the planet accumulates heat faster than it can radiate it away, and this process self-amplifies. Lead on the surface of Venus exists in liquid form. Tin melts. Zinc evaporates. If you have ever read descriptions of hell in religious texts, the authors clearly consulted the right sources, but temperature is just the beginning. The atmospheric pressure at the surface of Venus is about 92 atmospheres. For comparison, that is the pressure a person feels at about 1 kilometer deep in the ocean. Divers working at depths of several hundred meters spend hours in decompression chambers for their bodies to adapt to the changes in pressure. On Venus, there is no time or place to adapt. The pressure crushes instantaneously and totally. Furthermore, the atmosphere of Venus moves. The upper layers of clouds rotate around the planet in 4 Earth days, while the planet itself completes one rotation on its axis in 223 Earth days. This means that winds at cloud level reach speeds of 360 kilometers per hour. At the surface, they are significantly weaker, around a few kilometers per hour, but considering the density of the atmosphere, about 65 times denser than Earth's at the surface, even a gentle breeze on Venus has the force of a flowing river. Standing in it is like standing in a slowly flowing, invisible river that is also heated to a white-hot temperature. Now, about sulfur. The cloud layer of Venus consists of droplets of sulfuric acid with concentrations ranging from 75 to 96%. This is not a metaphor. This is not a poetic exaggeration. Sulfuric acid at such concentrations is used in industry for etching metals, producing fertilizers, and as an electrolyte in batteries. When it falls as rain, which happens regularly, it evaporates before reaching the surface because it is far too hot down there. The atmosphere of Venus is so rich in chemical compounds that it could enrich your lungs forever and completely free of charge. A rain of sulfuric acid hangs above a surface that one cannot walk on, under a sky that never brightens. This is Venus. The surface deserves special mention as it is beautiful in its own way, if viewed from a safe distance, a few light minutes away with a good telescope. Venus is geologically active, or has been active very recently in geological terms. There are volcanoes on the planet, and some of them seem to be active. Data collected by the European spacecraft Venus Express in the 2010s indicates thermal anomalies in the vicinity of several volcanic formations, which may suggest recent eruptions. The surface is covered in vast volcanic plains, dotted with calderas and lava flows. There are mountain ranges, like the Ishtar Terra in the north, which features Maxwell Mont, approximately 11 kilometers high, the highest point on Venus. If it weren't for the temperature, pressure, acidic clouds, and lethal atmosphere, this would be a magnificent place for mountain tourism. The chronicle of humanity's encounters with Venus is a story of stubbornness in the face of inevitable defeat, with the planet being the one to deliver that defeat, not the people. The Soviet Venus program is one of the greatest and least celebrated feats of engineering in the 20th century. The first spacecraft in the Venus series reached the planet in the 60s and were destroyed immediately. Atmospheric pressure crushed the bodies designed for earthly conditions long before reaching the surface. Soviet engineers learned from each loss. They made the bodies thicker, stronger, and more reliable. They added layers of thermal insulation. They refined parachute systems. They designed spacecraft meant to last not hours, but at least minutes, and considered that a victory. Venus 7 in 1970 became the first spacecraft to achieve a soft landing on the surface of another planet and transmit data from it. It operated on the surface for 23 minutes before temperature and pressure took their toll. 23 minutes was considered a triumph. Venus 9 and Venus 10 in 1975 were the first to send back photographs from the surface of Venus. Black and white images of a barren, rocky landscape, as if ripped from the set of some particularly bleak science fiction film. Sharp, angular stones, no wind erosion, no water, no life. Venus 13 in 1982 set a survival record, functioning on the surface for 127 minutes and transmitting the first color images. The sky above Venus turned out to be orange. The surface was dark gray with yellowish speckles, beautiful, and completely dead. American spacecraft operated differently, orbital missions. Pioneer Venus in 1978 conducted radar mapping of the planet's surface. Magellan, from 1990 to 1994, created a detailed radar map of the planet with a resolution of about 300 meters, uncovering thousands of volcanic formations, mountain ranges, and plains covered in solidified lava. It operated in orbit, smart and cautious, avoiding the risk of descent. Ultimately, it was deliberately sent into the atmosphere for the study of data on deceleration, and it, of course, burned up. That's how smart machines behave on Venus. They observe from a distance and don't venture closer. The most astonishing thing about Venus is how close it came to becoming our twin. It is almost the same size as Earth, almost the same mass, located just 41 million kilometers away from us at its closest point. In the solar system, there is no planet physically closer to us that is also infinitely far away in terms of habitability. Scientists sometimes refer to Venus as the warning planet, a living, scorching, sulfuric acid example of what happens to planets when the greenhouse effect spirals out of control. This warning is directed at us directly. For now, we pretend we don't hear. Venus is best observed through a telescope from the roof of your own home, holding a cup of tea while in good health, ideally on a clear night when it shines in the twilight. Beautiful, cold, safe from that distance. It will look back at you with its pearlescent clouds, and in that gaze, there is something almost welcoming. Don't believe a word of it. But if Venus is the hell we have reached and touched with our machines, the next world on our journey is a hell we are still comprehending only through distant observations. It's a world where the very concept of surface becomes a philosophical question. A world without solid ground beneath our feet, because there will also be no feet, but that's another story. The next stop is Jupiter. Story 2. Jupiter, the abyss that looks back. There's a moment in the film Interstellar when the ship comes into orbit around Saturn and the camera slowly pulls back, revealing the rings in all their glory, and you physically feel your own insignificance. Director Christopher Nolan knew exactly what he was doing. Nothing emphasizes human fragility better than the view of a truly massive celestial object. If he had filmed Jupiter up close, the movie would likely have turned into something utterly unbearable in its existential weight. Because Jupiter is not just a big planet. It is something fundamentally different in scale, in nature, and its degree of strangeness compared to everything we consider normal. Imagine that you are approaching Jupiter aboard an interplanetary spacecraft. At first, it looks just like on school posters and desktop backgrounds, a striped sphere in ochre, cream, and orange hues, with the mesmerizing swirl of the Great Red Spot in the southern hemisphere, a vortex larger than our Earth that has existed for at least 350 years. As you get closer, the details begin to emerge. Stripes that appeared static from a distance actually flow and swirl like cream and coffee made by some mad giant. The boundary between the light zones and the dark stripes is not merely a change in color, it is a border between atmospheric currents moving in opposite directions at hundreds of kilometers per hour. The closer you fly, the clearer it becomes. What looked like a beautiful pattern on a sphere is actually the grandest hurricane chaos in the solar system, captured in gas and preserved by gravity. Jupiter is the largest planet in our system, and this statement sounds banal only until you start delving into the numbers. However, we do not use numbers, we use images. If you were to take all the other planets in the solar system, Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, and combine them, Jupiter would still be roughly twice as heavy as that collective pile. More than 1,300 Earth-sized planets could fit inside it. It is so massive that its gravity significantly influences the orbits of other bodies in the solar system. It acts like a giant gravitational vacuum cleaner, pulling in comets and asteroids that might otherwise head toward the inner planets. Some astronomers refer to it as Earth's shield. Without Jupiter, our planet would be bombarded by comets thousands of times more frequently. One could say that we owe our existence to this gas giant. This does not prevent it from being one of the most deadly places in the solar system. The main problem with Jupiter is conceptual, and it is much deeper than it seems at first glance. Jupiter has no surface. At all. It is not a gas ball with a solid core that one could theoretically land on. Instead, it is gas that gradually becomes denser and denser as you descend, until it transitions into something for which there is no precise word in everyday language. Jupiter's atmosphere extends thousands of kilometers deep, and at some level, hydrogen under immense pressure transforms into a state that physicists call metallic hydrogen, a liquid that conducts electricity like a metal and is neither a gas nor a liquid in the usual sense. If you try to land on Jupiter, you will encounter neither solid ground nor even a clear boundary between the atmosphere and something else. You will simply be descending, slowly at first, then faster, until the pressure and temperature render the very notion of you irrelevant. It is worth starting with the upper layers of the atmosphere, as they are already unpleasant enough to make an impression. The temperature in Jupiter's upper atmosphere is around -140 degrees Celsius. It is cold, similar to a winter day on Mars, which means very cold, but theoretically manageable for a well-protected craft. However, this seemingly moderate climate is immediately compensated by fierce winds. The winds in Jupiter's atmosphere are among the most powerful in the solar system. At the equatorial latitudes, they reach speeds of 500 to 600 kilometers per hour. And this is not just gusts or temporary surges. This is a constant, unchanging, never-ending hurricane that has existed for centuries and even thousands of years. The Great Red Spot, this famous pinkish-red swirl in the southern hemisphere, is an anticyclone that has been present since the first telescopic observations in the 17th century, and within it, winds exceed 500 kilometers per hour around the entire perimeter. Over the past few decades, it has noticeably shrunk in size. Observations indicate that in the early 19th century, it was 4 times larger than it is now. But it has not disappeared, and seemingly, it has no intention of doing so. As one hypothetically descends deeper into the atmosphere, the temperature begins to rise. At a depth of about 70 kilometers from the upper cloud boundary, it reaches 0 degrees Celsius. Even deeper, 100, 200, 1,000. The pressure increases proportionally. What started as a few atmospheres transforms into hundreds, then thousands. The cloud layers alternate. The upper clouds consist of ammonia crystals, which give the planet its creamy white tones. Below are clouds of ammonium hydrosulfide, shaded in darker brownish-orange hues. Even further down, presumably, are clouds of water vapor and liquid water. Each layer presents its own chemical environment, its own range of pressures and temperatures, and its own mix of toxins and extreme conditions. Jupiter is also a source of monstrous radiation. Its magnetic field is approximately 14 times stronger than Earth's. It captures charged particles from the solar wind and accelerates them to colossal energies, forming radiation belts around the planet. The power of radiation in these belts is such that an unshielded person would receive a lethal dose within minutes, merely by being in orbit, without descending into the atmosphere. Even spacecraft with thick radiation protection gradually degrade in this field. Electronics malfunction, solar panels lose efficiency, and sensors fail. Orbiting near Jupiter is a slow death by radiation for any electronic equipment. The history of Jupiter exploration is a gallery of bold attempts and technical compromises. Pioneer 10 and Pioneer 11, launched in 73 and 74, became the first spacecraft to soar past the planet. They survived, but onboard sensors recorded radiation levels significantly exceeding predictions. Engineers realized that subsequent spacecraft would require serious shielding. Voyager 1 and Voyager 2 flew by in 79, transmitting the first detailed images of the Great Red Spot, atmospheric bands, and, unexpectedly, active volcanoes on Io, the closest of the large moons. This discovery became one of the major surprises of the space age, a volcanically active moon sustained by the tidal forces of Jupiter itself, which needs its interior as we need a piece of clay in our hands. The Galileo spacecraft became the most ambitious mission to Jupiter. It entered orbit in 1995 and operated for nearly 8 years, studying the planet and its moons. It was Galileo that confirmed the existence of a subsurface ocean beneath the icy surface of Europa, a moon that is now considered one of the most likely places for extraterrestrial life in the solar system. But Galileo's greatest achievement was the atmospheric probe launched in December 1995, directly into the clouds of Jupiter. The probe entered the atmosphere at a speed of around 170,000 kilometers per hour, faster than any other artificial object at that time, and experienced deceleration of 350 g. For comparison, fighter pilots lose consciousness at 9 g. The heat shield managed temperatures of up to 15,000 degrees Celsius. Then, the parachute deployed. The probe transmitted data for 58 minutes, diving deeper, into regions never reached by any human-made object. It recorded wind speeds exceeding 500 kilometers per hour, even in relatively calm areas. It measured temperature, pressure, and the chemical composition of the atmosphere. Then, at a depth of about 150 kilometers from the upper cloud boundary, the pressure reached 22 atmospheres, and the temperature soared to 153 degrees. Communication with the probe was lost. Not due to a technical failure, but simply because the structure could not withstand it. The probe continued to fall, deeper still, where pressures of thousands of atmospheres would turn any metal into something unrecognizable, but in silence. Its last data were sent in advance, before the end. The Galileo spacecraft itself was deliberately sent into Jupiter's atmosphere in 2003 to avoid contaminating its moons with earthly microbes in case of an accidental collision. Jupiter accepted it calmly, without ceremony. The modern Juno mission has been operating in a polar orbit since 2016 and continues to study the planet to this day, cautiously, avoiding the most hazardous radiation belts, designing its orbit so that each flyby over the poles is as informative as possible and as minimally suicidal. Juno discovered that the poles of Jupiter are covered with gigantic cyclones, geometric formations thousands of kilometers in diameter, ordered into neat polygons. 8 cyclones at the northern pole form a perfect octagon. 6 at the southern pole create a perfect hexagon. No one fully understands why, and that in itself is quite eerie. A planet that self-organizes its storms into geometric shapes seems to behave as if it has intention, or at least aesthetic preferences. Jupiter is best viewed through binoculars from your backyard on a clear night when it hangs low on the horizon, reflecting sunlight softly and almost cozily. Through a small telescope, you can even see its 4 largest moons, Io, Europa, Ganymede, and Callisto, which Galileo discovered back in 1610, and which became the first proof that not everything in the universe revolves around the Earth. Look at it from a distance, admire its bands. Watch as the great red spot slowly drifts across the disk. Don't think about what's inside. This will help you maintain your peace of mind. But while Jupiter overwhelms with its grandeur, its scale, pressure, and radiation, our next planet specializes in a far more sophisticated kind of death. It kills with temperature, but not with heat, rather with cold that exceeds anything we can replicate on Earth in a laboratory. Welcome to Neptune. Story 3. Neptune, the blue abyss at the edge of the known world. There is a particular sort of loneliness that polar explorers experience during the winter months, when the sun doesn't rise above the horizon for weeks, when the temperature outside makes any venture into the open an existential decision, when the closest other person is thousands of kilometers away, and communication with the larger world occurs through a crackling radio. This loneliness has its own weight, its own texture. Now multiply that feeling by 4,300,000,000 kilometers. That's how far Neptune is from the Sun at an average point in its orbit, and you'll start to grasp what this planet is about, not in a physical sense, in an existential one. From a distance, Neptune appears as if someone took the deepest, richest shade of blue from an artist's palette and filled an ideal sphere with it. Not light blue, not azure, not aquamarine, just blue, deep and dark like an ocean trench at dusk. This color results from the presence of methane in the upper layers of the atmosphere. Methane molecules absorb the red part of the solar spectrum and reflect the blue. The result is a planet that looks like a work of art, a blue pearl suspended in the darkness at the very edge of the solar system. If Neptune were smaller and warmer, it would have been immediately colonized by artists and poets. Fortunately for artists and poets, it is neither warm nor small. Neptune is the last of the 8 planets in the solar system when counted from the Sun. Pluto, as we know, was downgraded in 2006, a decision made by the International Astronomical Union, taken with that characteristic bureaucratic ruthlessness that sometimes grips scientific organizations. Neptune took its place as the outsider, the farthest one, the one who lives the furthest away. Light from the Sun takes about 4 hours to reach Neptune. For comparison, it takes 8 minutes to reach Earth. This means Neptune receives approximately 900 times less solar energy per square meter than our planet. The Sun from Neptune's surface, if there were a surface and if you could stand on it, would appear as just a very bright star, not a disk, not a luminary, just a point, slightly brighter than other points in the black sky. Yet, Neptune is not the coldest planet in the solar system. This is an important nuance that immediately raises the question, if it's not the coldest, then why is it on the list? The answer is simple. Neptune kills not just with temperature, it kills comprehensively, methodically, and with enviable variety of means. The temperature in the upper layers of its atmosphere is around -210 degrees Celsius, cold enough to freeze most gases that we on Earth take for granted. Nitrogen, oxygen, carbon dioxide. At such temperatures, they either condense into liquids or freeze into solid crystals. Neptune's atmosphere is primarily composed of hydrogen and helium, with traces of methane and other hydrocarbon compounds. This is not a mixture you would want to breathe, though, to be honest, at -210 degrees, the question of breathing becomes irrelevant quite quickly. But Neptune's main weapon is its winds. They are the most powerful in the solar system among all planets, and this statement takes a moment to fully grasp. The strongest winds in the solar system are not on Jupiter with its gigantic size, nor on Saturn with its elegant rings, but on the tiny, distant, forgotten by gods and humans, Neptune. Wind speeds in Neptune's atmosphere reach 2,100 kilometers per hour. That is supersonic speed. It is faster than an artillery shell flies. When Voyager 2, the only spacecraft ever to visit Neptune up close, flew by the planet in 1989, its cameras captured a dark spot in the southern hemisphere known as the Great Dark Spot. This was an anticyclone comparable in size to Earth, where winds reached those same 2,000 kilometers per hour. When the Hubble Space Telescope looked at Neptune again in 1994, the Great Dark Spot was gone. It had disappeared. It had dissipated. In its place, a new spot formed in the northern hemisphere. Neptune changes its storms like people change moods, swiftly and without visible warning. The nature of these monstrous winds remains a topic of discussion in planetary science. The paradox is as follows. Neptune is so far from the Sun that it receives an insignificant amount of solar energy. One would think that it should be solar energy that drives atmospheric currents, as happens on Earth, where uneven heating of the surface creates pressure differences and winds. But on Neptune, there is hardly any solar energy, and yet the winds are the strongest. The explanation lies in the planet's interior. Neptune radiates into space approximately 2 6/10 times more heat than it receives from the Sun. This internal heat, residual warmth from the planet's formation 4.5 billion years ago, is the main engine of atmospheric processes. Neptune heats up from the inside, like a dying fireplace, and it is this internal heat that creates convective currents, which propel the atmosphere to supersonic speeds. Neptune's structure is similar to Uranus, its nearest neighbor in the classification of ice giants. Beneath the atmosphere lies a layer of hot water, ammonia, and methane in a compressed state. This mixture is referred to by planetary scientists as hot ice, or supercritical fluid, because under tremendous pressure and high temperatures, water behaves completely differently than we are accustomed to. It remains liquid at temperatures where it should have turned to vapor, because the pressure prevents it from expanding. At the very center of Neptune, there is presumably a rocky core with a mass comparable to that of Earth. This core is heated to several thousand degrees Celsius, a temperature akin to the surface temperature of the Sun. Neptune is cold on the outside and scorching hot on the inside, and it is this contradiction that fuels its fury. The methane in Neptune's atmosphere warrants special attention, not only as a source of blue color, but also as a chemically active compound. Under the influence of solar ultraviolet light, methane molecules break apart and recombine into more complex hydrocarbon compounds, ethane, acetylene, ethylene, and others. These compounds gradually descend through the atmosphere, creating a chemical cycle that scientists have not fully deciphered. At great depths, under pressure of millions of atmospheres, carbon from methane can crystallize into diamonds, and these diamonds, according to some theoretical models, slowly sink into the planet's liquid mantle, settling on the rocky core. Neptune may literally be showered with diamonds from within. This is one of the most beautiful ideas in modern planetary science, and one of the least verifiable, considering the complete lack of ways to peek inside. Neptune's moon Triton deserves a separate discussion, as it is one of the strangest objects in the solar system. Triton is the only large moon in our system that orbits in the opposite direction to the planet itself. This is called a retrograde orbit, and it immediately signals to planetary scientists that this moon was not born here. It was captured by Neptune's gravity from the Kuiper Belt, an area of trans-Neptunian objects, at some point in the early history of the solar system. Triton orbits Neptune in reverse, slowly drawing closer. Gravitational tidal forces gradually lower its orbit, and in approximately 3.5 billion years, it will get close enough to be torn apart into rings, much like the objects that formed the rings of Saturn. The surface of Triton, at -235 degrees Celsius, is one of the coldest places measured in the solar system. But even there is a surprise. Voyager 2 discovered active geysers on Triton's surface, nitrogen geysers that shoot dark jets of gas up to 8 kilometers high. The energy source for them is the faintest sunlight that penetrates through a transparent layer of nitrogen ice and heats the dark material underneath. So insignificant is this heating that the surface remains at -235, but sufficient enough to create pressure that ejects gas into the thin atmosphere. Even on the coldest of known bodies, there is a small fury, a tiny protest against absolute zero. The Voyager 2 spacecraft, humanity's only envoy to have ever seen Neptune up close, flew past the planet in August 1989. By then, the spacecraft had already been in space for 12 years, having flown past Jupiter, Saturn, and Uranus. It was designed in the 70s, operating on computers millions of times less powerful than modern smartphones, and yet it accomplished a mission that has not been repeated since. It spent several hours near Neptune, passing about 4,900 kilometers from the upper cloud layer, and sent back thousands of images and gigabytes of scientific data before continuing its endless journey into interstellar space. Today, Voyager 2 is beyond the heliosphere, at the boundary where the influence of the solar wind ends and true interstellar space begins. It still transmits data, though its signal, traveling at the speed of light, takes more than 17 hours to reach Earth. Since Voyager, Neptune has not seen any earthly visitors. No orbital spacecraft, no probes, no flyby missions. This is not a coincidence or forgetfulness. It's physics. Interplanetary flights to the outer planets are only possible during specific mutual alignments of the planets, known as gravitational assists. The spacecraft accelerates using the gravity of one planet as a slingshot, jumps to the next, accelerates again, and so on. The Voyagers took advantage of a unique alignment of the planets that happens once every 175 years. The next similar alignment will occur in the 22nd century. Missions to Neptune without gravitational assists would take decades with current technology. NASA and ESA are developing conceptual designs for orbital missions to Neptune and Triton, but none have received funding for implementation. Neptune waits. It is in no hurry. Neptune is best observed through a telescope with an aperture of 25 centimeters or larger. At this magnification, it transforms from a point into a discernible disk with a characteristic blue hue. It is invisible to the naked eye, too distant, too dim. This might be seen as a metaphor for its nature overall. Neptune is secretive, remote, inaccessible. It does not shout about its danger as blatantly as Venus does, nor does it impose its authority with the scale of Jupiter. It simply resides at the edge, in cold and darkness, patiently stirring its 2,000-kilometer winds, demanding no one's attention. But there are planets that do not hide their deadliness. They display it openly, almost with pride. Our next world is just such a planet. It burns, it melts, it shimmers with molten rock beneath our feet and glass rain above our heads. This exoplanet, the first on our list, is far enough away that we can describe it without risking our own mental well-being. Welcome to HD 189,733b, a planet where it rains molten glass. Story 4. HD 189,733b, the planet where glass falls horizontally. There's a special genre in science fiction. Let's call it beautiful death in space. It's when a director or writer creates a world so visually mesmerizing, so aesthetically perfect in its otherness, that the viewer or reader experiences both admiration and horror simultaneously. Two feelings that rarely coexist so comfortably in everyday life. Planet HD 189733b is just such a world. It is blue. Not blue like Neptune, cold, distant, and melancholic, the blue of an ice giant. No, this is a different kind of blue. Rich, almost metallic, like cobalt or deep indigo, the blue of molten heat. Better yet, the blue of searing temperatures. A world where surface temperatures reach 1070 degrees Celsius. This is the bluest exoplanet known to us, and one of the deadliest. The HD 189733 system is located 63 light-years from Earth, in the constellation Lyra, if you're curious to point a telescope that way and ponder the fragility of existence. 63 light-years is both far away and, in cosmic terms, practically next door. The light from this planet that you see through the telescope right now left there in 1960, when humanity hadn't sent a single probe into outer space. The planet was discovered in 2005 using the transit method. Astronomers noticed that the parent star slightly dimmed at regular intervals, indicating that something large and round was regularly passing across its disk. This large and round object turned out to be a gas giant, roughly 13 times more massive than Jupiter, and its orbit was such that astronomers immediately understood this is a very bad place. The orbit of HD 189733b takes 2 2/10 Earth days. 2 days, and the planet completes a full revolution around its star. For comparison, Mercury, the closest planet to the Sun in our system, takes 88 days to orbit it, and is already considered a catastrophically hot place. HD 189733b is 30 times closer to its star than Earth is to the Sun. The distance between the planet and its star is so small that they are connected by gravitational tidal forces. The planet is tidally locked, always showing one side to the star, just like the moon always shows one side to Earth. This phenomenon is called tidal locking. One side of the planet is in eternal daylight, scorching, illuminated, ablaze. The other side is in eternal night. Between them lies a thin strip of perpetual twilight, the terminator, where the temperature is theoretically a bit lower. Theoretically. The atmosphere of this planet is what truly makes it unique in the gallery of cosmic horrors. It is rich in silicates, those very compounds of silicon and oxygen that make up Earth's rocks, sand, and, essentially, glass. At temperatures above 1000 degrees, silicates vaporize on the day side of the planet and rise into the upper layers of the atmosphere. There, they are picked up by winds and carried to the night side, where the temperature is somewhat cooler. The word somewhat here indicates a difference of about 200 to 300 degrees, still over 600 degrees Celsius, which is sufficient to melt lead, tin, zinc, and most known metals. On the night side, silicates condense, transform back from gas into tiny solid or semi-liquid particles, and fall as precipitation. This is the rain of molten glass, not a metaphor, not a literary exaggeration, a literal silicate rain, with glass droplets and crystals the size of a few microns falling from clouds and immediately evaporating back into the searing atmosphere before reaching, if there is anything at all, what can be called a surface. Now, let's talk about the winds, because without them, this story would be incomplete. The wind speeds in the atmosphere of HD 189733b reach 8,700 kilometers per hour. We just mentioned Neptune with its 2,000 kilometers per hour and called those the most powerful winds in the solar system. Here, they are 4 times faster. That's about 7.5 times the speed of sound. Sound in the atmosphere of this planet, if there were anything capable of producing and perceiving it, would move slower than the wind. The glass rain doesn't fall downward. It travels horizontally, almost parallel to what could somewhat arbitrarily be called the surface, carried by these monstrous currents of the atmosphere. Silicate particles flying at nearly 9,000 kilometers per hour are not rain in the usual sense. This is sandblasting taken to the absolute. This is what happens to matter when physics decides to show what it is truly capable of without being constrained by the conventions of a temperate climate. The blue color of the planet, what first catches the eye and appears so beautiful in illustrations, is a result of these silicate particles in the atmosphere. They scatter the blue part of the spectrum of starlight, just as water droplets in Earth's atmosphere scatter sunlight, making the sky blue. Only the scales are incomparable. The entire planet looks blue because its atmosphere is saturated with microscopic glass particles that eternally swirl in eddies at speeds that obliterate any concept of visiting this place in person. How did astronomers learn about the glass rain? That in itself is a story worthy of a separate tale, a story of how human ingenuity allows us to study worlds that we can physically never reach. The method is called transmission spectroscopy. When a planet passes in front of the disk of its star, some starlight passes tangentially through the planet's atmosphere. Different chemical compounds absorb light at various wavelengths, leaving distinct fingerprints in the spectrum, absorption lines. By analyzing which wavelengths are missing in the light that passes through an atmosphere, astronomers can determine the chemical composition of that atmosphere from a distance of 63 light-years. Data obtained by the Hubble Space Telescope in 2013 revealed the presence of silicate particles in the upper layers of this atmosphere and helped confirm a model of silicate rain that theorists have been developing since the planet was discovered. The same Hubble allowed for another discovery that added the final touch to the planet's portrait of grim perfection. In 2012, astronomers observed the planet's transit in the ultraviolet range and recorded something unexpected. The planet's atmosphere is actively escaping into open space. Its parent star, HD 189,733, an orange dwarf of class K, bombards the planet with powerful X-ray and ultraviolet radiation in amounts that are 1,000,000 times greater than what Earth receives from our Sun. This radiation heats the upper layers of the atmosphere to temperatures at which atmospheric gas reaches speeds sufficient to overcome the planet's gravity and simply escapes. The planet loses between 100 and 600 tons of material every second, evaporating into space, leaving behind a tail resembling that of a comet. Over 5 billion years, the star has already evaporated a significant portion of the planet's original atmosphere. In the next 5 billion, it will evaporate even more. This brings us to the concept that planetary scientists refer to as hot Jupiters, a class of exoplanets to which HD 189,733b belongs. Hot Jupiters are gas giants that orbit their stars at distances tens of times smaller than Mercury's distance from the Sun. Their existence has puzzled planetary scientists for a long time because, according to standard models of planetary system formation, gas giants are expected to form far from their star, where it is cool enough for volatile substances to condense. It turns out that after formation, they can migrate. Gravitational interactions with the protoplanetary disk and with other planets gradually change their orbits, pulling them closer to the star. This is called planetary migration, and this process is catastrophic for anything in its path. A migrating gas giant sweeps away all smaller bodies from its orbit, gravitationally disturbs the orbits of other planets, sometimes ejecting them from the system into interstellar space. Systems with hot Jupiters are generally not good places for small, cozy, Earth-like planets to exist. A hypothetical expedition to HD 189,733b is a thought experiment that physics interrupts at every step. Let's assume you somehow overcame 63 light-years, which, with current technologies, would take several 100,000 years, but let's set that aside. Imagine you've entered orbit. Already here, the X-ray and ultraviolet radiation from the star would start methodically destroying any unprotected electronics. The planet's magnetic field, which should exist given its size even though we haven't measured it directly, would likely capture some of that radiation, but not all of it. Attempting to enter the atmosphere would mean an immediate encounter with winds traveling at 8,700 kilometers per hour and rain made of silicate particles, which would process the surface of any craft with the efficiency of industrial abrasives in just a few seconds. Temperatures above 1,000 degrees would turn most structural materials into liquid or gas. This is not a world worth visiting for a polite call. Yet, it is precisely such planets that are among the most studied exoplanets because they are convenient to observe. Their large sizes, frequent transits, and proximity to their star make them ideal objects for transmission spectroscopy. It is a bitter irony. We know more about HD 189,733b than many bodies in our own solar system, simply because it is so extreme that it is easily detectable and easily studied through its own excesses. HD 189,733b is best understood as an abstraction, a beautiful cobalt blue dot on a star map that you can admire in illustrations in scientific journals, reveling in its color while trying not to think about what lies behind that blueness. It is a planet artist painted with the deadliest pigment that exists in nature, molten glass in hurricane winds. And now, from the heat to another form of extremity, the next planet doesn't scorch with glass and doesn't crush under 90 atmospheres. It operates more subtly. It literally tears apart. With tidal forces capable of stretching and shredding everything that enters its gravitational influence. Our next destination is Io, the most volcanically active body in the solar system, living proof that gravitational violence can create landscapes that take your breath away. Story 5. Io, the heart that cannot stop burning. Imagine a pizza. Not because it's funny, though it is somewhat humorous, but because that's how Louis Soderblom, a geologist from the U.S. Geological Survey, described Io when he saw the first detailed images sent back by Voyager 1 in 1979. Yellow, orange, red, white, black, spots and streaks, drips and splotches layered together in a completely chaotic, almost grotesque pattern. A pepperoni pizza made by some mad chef who used molten sulfur instead of tomato sauce, frozen sulfur dioxide instead of cheese, and crust that is permeated by magma breaking through in more than 100 points at the same time. If Dante were writing the Divine Comedy in the age of space telescopes, Io would undoubtedly take a prestigious place in his Inferno, likely several circles at once. Io is the third largest of Jupiter's 4 Galilean moons and the innermost of them. It was discovered by Galileo Galilei in January 1610, along with Europa, Ganymede, and Callisto, 4 points that he observed through a primitive telescope, which moved in a way that immediately suggested to him that they were orbiting Jupiter rather than Earth. This discovery became one of the nails in the coffin of the geocentric model of the universe, costing Galileo a great deal of trouble with the Inquisition. 4 centuries later, when Voyager 1 transmitted the first detailed images of Io, it turned out that this moon is the most geologically active body in the entire solar system, including Earth itself. Galileo would surely appreciate the irony. The volcanic activity on Io was theoretically predicted just days before Voyager confirmed it. In March 1979, literally on the eve of Voyager 1's flyby, a young researcher named Stanton Peele and his colleagues published a paper in the journal Science, predicting that Io must be volcanically active based on tidal heating calculations. When Voyager's images showed active volcanoes a few days later, it became one of the rarest instances in the history of planetary science where theory outpaced observation by a matter of just days. Peele, according to eyewitnesses, was as astonished as anyone else. His own paper was still hot off the press when the observations confirmed each word. The mechanism that turns Io into an endlessly burning fireball is tidal heating, and it deserves a detailed explanation because it exemplifies how gravity can generate heat from literally nothing. Io is in orbital resonance with 2 other Galilean moons, Europa and Ganymede. This means that for every 1 orbit Ganymede makes around Jupiter, Europa completes 2 orbits, while Io makes 4. This geometrically precise synchronization of orbits prevents Io from settling into a perfectly circular orbit. The gravitational pulls from Europa and Ganymede periodically stretch Io's orbit into an ellipse. The varying distance to Jupiter means that the gravitational tug of the gas giant changes constantly, sometimes stronger, sometimes weaker. For Io, this means the following. Jupiter literally squishes it like you would a rubber ball in your hands. The planet pulls on the near side of the moon more strongly than on the far side, creating a tidal bulge, a protrusion that shifts across its surface as Io moves along its orbit. The crust of the moon rises and falls by up to 100 meters with each rotation. 100 meters is the height of a 30-story building that rises and disappears beneath your feet every 42 hours. The friction between layers of rock generates a colossal amount of heat, approximately 2.5 times more than all the internal heating of the Earth combined. Io emits around 100 trillion watts of thermal power. This exceeds the total energy produced by humanity over several years. All of this power comes from pure gravitational friction, as the colossal Jupiter simply cannot leave its tiny moon in peace. The result of this geological violence is a surface that is the youngest in the solar system. There are no meteorite craters on Io, none at all, 0. It is not because Io is not subjected to meteorite bombardment. It is, regularly. The volcanic activity is just so intense that it covers the entire surface with a new layer of volcanic deposits approximately every 100 years. Meteorite craters simply do not have time to remain. They are buried under lava and sulfur deposits before the next probe can photograph them. Geologists studying Io work with a surface that is, on average, no more than 100 years old. In geological terms, that was literally yesterday. It is still warm and steaming. The volcanoes on Io are divided into several types, and each deserves a separate page in the catalog of geological anomalies. The most powerful are called paterae. These are immense calderas filled with lakes of molten lava. Some of them reach over 200 kilometers in diameter, comparable in area to a small European country. Leupatera, one of the most studied, contains a lava lake covering more than 200 square kilometers, with a constantly renewing crust of solidified lava that occasionally tips over and sinks below the surface, exposing fresh molten magma underneath. The process resembles a conveyor belt. The cooling crust moves from the center to the edges, where it collapses and melts down again. This happens slowly, almost majestically, and continuously. The mountains on Io are a separate mystery. Unlike mountains on Earth, which form due to tectonic collisions or volcanic eruptions, the mountains on Io arise differently. The continuous accumulation of new volcanic deposits gradually increases the load on the crust, and at some point, blocks of the crust begin to settle under their own weight, while neighboring blocks are pushed upward, forming steep, fractured ridges. The tallest mountain on Io, Bosal Mons, reaches a height of about 18 kilometers. In comparison, Everest is around 8.5. However, Bosal Mons is not a volcano in the traditional sense. It is an uplifted block of crust surrounded on all sides by flows of lava and sulfur plains. It stands like an absurd monument amidst absolute geological chaos. The most famous volcano on Io is Pele, named after the Hawaiian goddess of volcanoes. This name is well deserved. Pele generates one of the largest volcanic plumes in the solar system. The ejection of material rises to heights of up to 300 kilometers above the surface and spreads over an area with a diameter of about 1,200 kilometers. The substance that Pele ejects into space is rich in short-chain sulfur compounds, which give the surface around the volcano its characteristic dark red and orange hues. Pele works continuously. It has been active during every observation since 1979, although the intensity of its activity varies. There is something almost alive about this unstoppable, rhythmic, centuries-old activity, as if the planet is breathing, and each breath rises 300 kilometers into the sky. Another remarkable volcano is Tvashtar, discovered by the Galileo spacecraft in the year 2000. Its images, taken in November of that year, revealed something that planetary scientists did not expect to see. Enormous lava fountains reaching heights of about 1.5 kilometers, arranged in an arc 25 kilometers long. Lava fountains are a phenomenon known on Earth from Hawaiian and Icelandic volcanoes, but they have never reached such scales. On Io, the reduced gravity, around 1/6 of Earth's, allows lava to soar significantly higher than on our planet. Additionally, the lower viscosity of some types of juvenile lava, rich in sulfur compounds, enables it to flow quickly and far. When New Horizons flew past the Jupiter system in 2007 on its way to Pluto, it captured images of Io, where Tvashtar was active once again. And this time, its plume reached a height of 330 kilometers, resembling a giant umbrella or jellyfish lifted above the surface. The temperature of the lava in Io's most active volcanoes reaches 1,800 degrees Celsius, hotter than most lava on Earth, and corresponding to a composition close to ultramafic magmas, komatiites, which were common on early Earth over 3 billion years ago. Io therefore acts as a sort of geological time machine. Its activity resembles what occurred on our own planet during the Archean era, when the crust was thin, magma was hot and mobile, and the surface was constantly being reshaped. By studying Io, planetary scientists investigate what Earth might have been like at the dawn of its history. Radiation adds the final grim touch to the portrait of Io. As mentioned earlier, Jupiter is surrounded by powerful radiation belts. Io is situated right in the most intense part of these belts, constantly bathing in streams of charged particles. The radiation dose at Io's surface is about 3,600 rads per day. A lethal dose for a human is around 500 rads total. This means that an unshielded person on Io's surface would receive a fatal dose in approximately 3.5 hours. Io's atmosphere is extremely thin, primarily composed of sulfur dioxide, providing no radiation protection. Io manages to threaten life in several ways, by melting you with lava, suffocating you with sulfur gases, roasting you with radiation, while looking like a forgotten pizza from the freezer. The Galileo spacecraft studied Io for several years, making periodic flybys and getting closer each time. Every flyby near the planet struck the onboard electronics. The radiation belts of Jupiter gradually damaged the instruments. By the end of the mission, some tools were out of order. The electronics degraded under the relentless radiation bombardment. Nevertheless, Galileo continued its work for as long as technically possible, transmitting data about volcanoes, lava lakes, and mountains right up to the mission's end in 2003, when it was directed into Jupiter's atmosphere. Io is best studied through the lens of a telescope or in images from probes, a bright yellow, orange, and red sphere carelessly spinning around its enormous master. From a distance, it appears almost endearing. Almost. If you happen to gaze upon it, consider that at this very moment, while you read these lines, dozens of volcanoes are erupting on its surface, lava lakes are splashing over the edges of calderas, and sulfur geysers are shooting higher than any airplane has ever flown above the Earth. This is happening right now, continuously. And it will continue for billions of years until Jupiter releases it or until Io's orbit changes enough that tidal heating weakens. Until then, Io will continue to burn. It simply has nowhere else to go. But there are worlds where the threat doesn't come from deep within or from the atmosphere, but literally from the sky. Our next world kills with light. More precisely, with what a star does to its nearest planet when it decides that the planet has become too complacent. Welcome to Kepler 70b, a planet that orbits inside its star, or nearly inside. In this case, they are the same thing. Story 6. Kepler 70b, the planet that survived its star and regretted it. There is a particular kind of tragedy that the Greeks called peripeteia, a sudden reversal of fortune, where what seemed a salvation turns into a catastrophe. A hero fleeing one fate is caught by another, even harsher. Kepler 70b is a planet that literally survived the death of its star. It passed through fire, in the most literal physical sense of the word, and emerged on the other side. This should have been a story of triumph, survival, a victory of matter over the destructive power of a dying star. But the universe is a poor scriptwriter when it comes to happy endings, and what happened to Kepler 70b after its miraculous escape is arguably one of the darkest stories in the catalog of exoplanets. It survived, only to slowly die further, in conditions that make the concept of survival merely academic. The Kepler 70 system lies about 3,900 light-years away from Earth, in the constellation Cygnus. This is far even by the standards of our catalog of exoplanetary horrors, so far that the light we observe from there now left when there was still no writing, agriculture, or most of what we call civilization on Earth. The parent star of the system, a Class B star, once hot, massive, and bright, has gone through one of the most dramatic transformations that stars experience at the end of their life. It expanded into a red giant, engulfing its inner planets, or nearly engulfing them, before shedding its outer layers and collapsing into what it is now, a subdwarf, a hot star that has gone through its apocalypse and remains to burn as a compact, extremely hot remnant. The surface temperature of this star today is about 27,000 degrees Celsius. In comparison, the surface of our Sun is around 5,500 degrees. Kepler-70 burns 5 times hotter than the Sun and shines about 250 times brighter. The planet Kepler-70b most likely formed at a significantly greater distance from the star, where conditions were suitable for the formation of solid bodies. When the star began to expand into its red giant phase, the planet was probably pulled into the expanding stellar atmosphere. This should have destroyed it. Yet, it was not completely obliterated. The planet passed through the layers of the red giant, lost a colossal amount of mass, and was stripped down to its rocky core. And when the star collapsed back into a subdwarf, the planet ended up in an orbit that takes about 5.5 hours to complete. 5.5 hours is the full revolution around the star. This means the distance between the planet and the star is approximately 870,000 kilometers. The radius of our Sun is about 700,000 kilometers. Thus, Kepler-70b orbits around its star at a distance of about 1.2 solar radii from its center. If this were our system, the planet would be inside the Sun, deep within its core. In relation to Kepler-70, it is located about 170,000 kilometers from the surface of the star, a little less than half the distance from Earth to the Moon. This distance defines the surface temperature of the planet, and this is where the story becomes truly unbearable. The temperature on the illuminated side of Kepler-70b is around 7,200 degrees Celsius. Let that number, more specifically the phrase 7,200, settle in your mind. The surface temperature of our Sun is 5,500 degrees. This means that the surface of Kepler-70b is hotter than the surface of most stars, including our Sun. A planet that is hotter than the star it orbits, hotter than many stars in the universe. This is not just very hot. This is a category in which the very concept of surface requires rethinking. At 7,000 degrees, most rocks do not just melt, they vaporize. Silicon, magnesium, iron, calcium, all the key components of silicate rocks turn into gas. This means that if Kepler-70b has a surface, and it must have something since it is a solid body, then this surface is constantly vaporizing. Rocks are boiling. Stone turns into steam. The atmosphere of the planet, if you can call it that, consists of evaporated rock, vapors of silicon, magnesium, iron, and other heavy elements that transition into a gaseous phase at such high temperatures. This is referred to as a magma ocean with a mineral atmosphere, a concept that planetary scientists are developing for the hottest rocky planets. The planet literally evaporates itself, and this vapor forms something akin to an atmosphere, only instead of hydrogen or nitrogen, it is made up of molten rock that has been heated to a gaseous state. This boiled in its own juice world receives a radiation flow from its star that exceeds what Earth receives from the Sun by 80,000 times. 80,000 times. Every square centimeter of the surface of Kepler-70b receives as much energy as thousands of square centimeters of Earth's surface would, if Earth had no atmosphere and all solar energy fell directly onto its surface. The planet glows in the infrared range. This was one of the methods that astronomers used for its detection and characterization. It is so hot that its own thermal radiation can be detected. The discovery of the Kepler-70 system was announced in 2011 based on data from the Kepler Space Telescope, the very telescope that methodically observed a section of sky in the constellation Cygnus from 2009 to 2018 and recorded how the brightness of stars slightly changed as planets passed by. This is how the system was discovered. Astronomers noticed tiny, regular decreases in the brightness of the star Kepler-70, with periods of about 5.5 hours and about 2 days. These were signs of two planets, Kepler-70b and Kepler-70c. Both are in orbits that literally exist at the surface of the star. Both have survived the red giant phase of their star. Both are now slowly evaporating. The history of the discovery of the system was accompanied by significant discussions within the scientific community, and this is also part of its portrait. A number of astronomers expressed doubts as to whether the candidates for planets were indeed planets or artifacts of the star's own pulsation. A subdwarf star can pulsate, slightly change its brightness at regular intervals, and these pulsations can theoretically mimic transit signals. The debate continues to this day, and some researchers hold a skeptical position regarding the nature of Kepler-70b. Nevertheless, the initial interpretation, two planets that survived after the red giant phase, remains the main one in the literature, and this is what makes the system so captivating. If the planets are real, their history is unprecedented. If they are artifacts, it means the star is so extreme that its own oscillations mimic the orbital periods of possible planets. In any case, the system is intriguing. What will happen to Kepler-70b next? The subdwarf around which it orbits continues to slowly cool down and contract. In the end, over timescales of billions of years, it will become a white dwarf, a cold and dim remnant of what was once a massive star. By that time, almost nothing will remain of Kepler-70b. The continuous evaporation of its surface, the relentless pressure of stellar wind, and harsh radiation will methodically wear down the planet, peeling it layer by layer, like plaster from an old wall. The planet, having survived the expansion of its red giant phase and remaining as a solid body, will slowly be consumed by its star, now smaller but still hot enough to continue the work of destruction. This is not death in a sudden cataclysm. It is a slow, unhurried, inevitable disappearance. A hypothetical observational mission to Kepler-70b, not an expedition nor even a flyby, would encounter problems upon approach. The harsh ultraviolet and X-ray radiation from the subdwarf, combined with the stellar wind carrying particles with immense energies, would require radiation protection of a fundamentally different level than anything ever constructed for exploring bodies in the solar system. At several million kilometers from the system, the spacecraft would start receiving doses of radiation many times greater than anything encountered by Earth probes near Jupiter. As it drew closer to the planet, a few 100,000 kilometers away, detectors would pick up a characteristic glow. The planet indeed glows, heated to a temperature brighter than the surface of the Sun, emitting in the visible range, not with the orange or red light of molten metal, but with a yellow-white, almost blinding radiance. It would be a sight unparalleled in human experience, a planet glowing like a star, spinning around a star at nearly touching distance, both objects blazing in space against the backdrop of black emptiness. The Kepler-70 system is a reminder that the universe makes no distinctions between planet and star in the sense that matters for survival. These are categories of observers. Humans devise these words to organize what they see. The universe sees only mass, temperature, pressure, and gravity. Kepler-70b has enough mass to maintain its shape, for now, but it is hotter than most stars and evaporates faster than it cools. In the coordinate system of physical laws, it is not a planet fighting for survival. It is simply matter gradually transitioning from one state to another, with no drama, no conclusions. With the complete indifference that is the hallmark of the universe, Kepler-70b is better observed as a data point on a brightness curve, a beautiful notch appearing regularly every 5.5 hours. Abstract, safe, not requiring one to imagine being hundreds of thousands of kilometers from a surface that is hotter than the sun, aboard a ship that melts faster than one could regret the decisions made. From the intense heat to the blinding white glow of the cosmos, we move to a planet that kills in a completely different way, not with heat, but with darkness. Not with evaporation, but with rupture. Our next world is a planet orbiting a neutron star, where space itself is permeated with radiation so powerful that the laws of physics start to behave indecently. Welcome to PSRB 127+12, the first exoplanet ever discovered orbiting a dead star. Story 7. PSRB 127+12, the planets of the Death Lighthouse. There is a special kind of silence in old lighthouses. When the fire is extinguished, the mechanism is stopped, and only the wind wanders through the shattered glass of the lantern room. A lighthouse without a flame is just a tower. Useless, cold, forgotten. But imagine a lighthouse whose flame has not been extinguished. It has simply changed its nature. Instead of warm yellow light, there are cones of harsh X-ray radiation rotating in space at a frequency of 160 times per second. Instead of warning sailors of dangerous rocks, it warns the entire universe that a star has died here, and it did not die quietly. This is the pulsar PSRB 127+12, located about 1,000 light-years from Earth in the constellation Virgo, and it has planets orbiting around it. 3 planets, the first exoplanets ever confirmed by science, the first worlds beyond the solar system that we confidently know exist. And each of them is one of the most deadly places in the known universe. The story of the discovery of the system begins with Polish astronomer Alexander Wolszczan and his Canadian colleague Dale Frail, who in 1991 were working with data from the Arecibo radio telescope, a gigantic radio dish 300 meters in diameter, carved into the limestone hills of Puerto Rico. Wolszczan analyzed signals from the pulsar PSRB 127+12 and noticed something extremely unusual. The pulsar's pulses came with tiny but perfectly regular deviations from the expected schedule. A pulsar is a neutron star spinning at a monstrous speed and emitting narrow beams of radio waves that pass through our observation point with each rotation, like a lighthouse beam. These pulses are incredibly regular, more accurate than most atomic clocks, because they represent the mechanical result of the rotation of a very dense, very stable object. Any deviation from the schedule means something is affecting the pulsar's movement. Wolszczan and Frail spent almost a year checking their data and ruling out alternative explanations before they decided to publish their conclusion. The deviations in the pulses are explained by the gravitational influence of planets orbiting the pulsar. The planets tug the pulsar back and forth, and this shift in the source of the signal alters the timing of the pulses by a fraction of a millisecond. It is this fraction of a millisecond that Wolszczan detected in the Arecibo data. In February 1992, they published a paper in the journal Nature announcing the discovery of the first planets beyond the solar system. Until now, the existence of exoplanets had been a subject of theoretical speculation and unsuccessful searches for decades. Wolszczan and Frail found them where no one expected, around a dead star, an object whose very existence stands as a monument to catastrophe. To understand what a pulsar is, one must first grasp the concept of a supernova explosion, as a pulsar is a direct consequence of it. When a massive star, significantly heavier than the Sun, exhausts its nuclear fuel in its core, the core collapses under its own gravity in a fraction of a second. In that brief moment, an object the size of a planet shrinks down to one with a diameter of about 20 kilometers. All the mass comparable to that of the Sun is packed into a volume the size of a small city. The density of the material becomes so immense that electrons and protons are pressed together, forming neutrons, hence the name neutron star. The outer layers of the star, unsupported by the core, crash down upon it, bounce off, and explode into space at a speed of about 30,000 kilometers per second in a supernova shockwave. This explosion, one of the most powerful events in the universe after the Big Bang, shines brighter than an entire galaxy for several weeks. The neutron star left behind after the explosion spins rapidly because angular momentum is conserved in the process of collapse. This small, dense object rotates much faster than a large, loose one, similar to how a figure skater speeds up their spin by pulling their arms close to their body. The pulsar PSRB 257+12 rotates 160 times per second. This phenomenon is called a millisecond pulsar, and such a high rotation speed indicates that this pulsar is a special type. It has been sped up to this velocity through the accretion of material from a companion in a binary system. In other words, there used to be another star nearby, which gradually fed matter to the pulsar, increasing its spin. This second star was either completely consumed or ejected from the system, and the pulsar was left alone, spun up to 160 rotations per second, emitting cones of radio waves and X-rays like a lighthouse gone mad from speed. The planets around this pulsar, 3 in total, designated A, B, and C, are comparable in size to Earth and the Moon. Planets B and C are slightly heavier than Earth and orbit at distances roughly corresponding to the orbits of Mercury and Venus in our own system. Planet A is smaller, about the size of the Moon, and orbits closer to the pulsar. All three planets rotate in a plane nearly identical to the line of sight. This is why Wolshan was able to detect their gravitational influence on the pulsar so precisely. How these planets formed is a question that is still under discussion. There are two main scenarios. The first is that the planets existed before the supernova explosion, survived the catastrophe, likely losing much of their atmosphere and undergoing radical changes to their surface, and continue to orbit what remains of their star. It would be an astonishing case of survival. Planets that have endured an explosion powerful enough to briefly overshadow an entire galaxy. In the second scenario, planets formed after the explosion, either from the remnants of a companion star that was destroyed, or from the disk of material left over after a supernova event. In this case, the planets are the children of catastrophe, literally formed from the ashes of a dead star. Neither scenario makes them any more suitable for the existence of life. The radiation environment around the pulsar PSRB 257+12 is one of the most extreme known in our universe. The pulsar emits narrow beams of radio waves, X-rays, and gamma rays every 6 milliseconds, 160 times a second. These beams sweep through the surrounding space. The planets in the system are close enough to receive a significant portion of this radiation with each rotation. The dose of X-rays and gamma radiation on the surface of planet B, for example, is thousands of times greater than the lethal dose for any known organism, and this is constant, not just when passing through the radiation beam, but continuously, because the pulsar is a powerful source of background X-rays in all directions, in addition to its directed beams. Furthermore, the pulsar generates a powerful stellar wind, a stream of charged particles with high energies, relativistic electrons and positrons, that disperses in all directions. This wind creates a nebula around the pulsar, an area of space filled with high-energy particles, known as a pulsar wind nebula. The planets in the system are immersed in this nebula. Their surfaces are continuously bombarded by particles with energies that render the concept of atmosphere as protection meaningless. The atmosphere, if it exists on these planets at all, would have been completely ionized and gradually blown away by the stellar wind over thousands of years. The planets are likely barren, stripped down to their rocky cores, devoid of any volatile compounds, desiccated and irradiated to a state where the chemical reactions fundamental to life are simply impossible. The surface temperature of the planets is not determined by thermal radiation from the pulsar. The neutron star, despite its monstrous surface temperature of several million degrees, is a very small object and emits much less heat than a normal star. The primary source of heating for the surface of the planets is the high-energy radiation and particle bombardment. As a result, the surfaces of these planets are likely not overly hot compared to other bodies in our guide. They may be several hundred degrees above absolute zero, ranging from -100 to a few hundreds of degrees Celsius, depending on the distance from the pulsar and local activity. But the temperature here is the least of their problems. It is not the heat that is deadly. It is the very fact of being near an object that is one of the most energetic sources of radiation in the galaxy. A neutron star is an object about 20 kilometers in diameter with a mass comparable to that of the Sun, possessing a surface gravity that is approximately 100 billion times stronger than that of Earth. This means that on the surface of a neutron star, you would weigh 100 billion times more than you do on Earth. With an Earth weight of 70 kilograms, your weight on a neutron star would be 7 trillion tons. This gravity is so extreme that atoms can no longer maintain their usual structure. Electron shells become flattened, and matter transitions to a neutron state. The very idea of standing on the surface of a neutron star is physically meaningless. No known matter in our universe can exist in its usual form under such a gravitational field. The planets in this system are far enough from the pulsar that its gravity does not tear them apart. They are beyond the Roche limit, that critical distance within which the tidal forces of the pulsar would pull them into a ring of debris. But that is the only good news. Everything else, X-rays, gamma radiation, relativistic particles, stellar winds, a magnetic field trillions of times stronger than Earth's, renders these planets utterly uninhabitable for any known form of life. Even the most extreme organisms on Earth, bacteria living in sulfuric hot springs and tardigrades surviving the vacuum of space, would not last even a fraction of a second here. The discovery of planets around PSRB 257 plus 12 was initially met with enthusiasm, quickly replaced by contemplation. The first reaction, "We found other planets, we are not alone in the universe," gave way to a more sober realization. We found the most inhospitable planets imaginable. It's like searching for neighbors in a communal apartment, only to discover that the neighbors are a death beacon spinning at 160 rotations per second, illuminating the space with X-rays. Technically, neighbors have been found. Practically, it would have been better if they hadn't. The PSRB 257 plus 12 system is better viewed as a historical footnote, an initial chapter in the chronicle of exoplanet discovery, important for its existence rather than what it offers as a destination. This discovery shifted the paradigm. If planets can exist near a pulsar, a body whose very existence is a consequence of a cataclysm of planetary scale, then planets could exist practically anywhere. This thought is both inspiring and frightening. It is inspiring because planets are far more widespread in the universe than we thought. It is frightening because most of them, it seems, are just like this. From a dead star with its blinding cones of radiation, we move to a world where death comes in a different form, not in a stream of radiation, but in absolute cold and absolute darkness. Our next destination is an orphan planet, wandering through interstellar space, without a star, without warmth, without light. A planet which a gravitational cataclysm has expelled from its home system and left to drift in the darkness between stars, perhaps forever. Welcome to a world with no dawns at all. Story 8. Orphan Planet, Eternal Night Without an Address. There's a children's scary story told in various cultures with different variations about what will happen if the sun goes out. Kids ask, "What will happen to us if there is no sun?" Adults respond evasively because the honest answer is both too simple and too cruel at the same time. Without the sun, Earth will turn into a frozen rock drifting in darkness, and it will happen quickly enough that no one will have time to adjust to the new conditions. This is precisely the situation for orphan planets. It's not just a scary story or a hypothetical scenario for them. This is their only reality, whether from the very beginning or after a catastrophic event that tore them from their home system and sent them on an endless solitary voyage through the interstellar ocean. Orphan planets, or as they are referred to in scientific literature, free-floating planets, substellar objects, planemos, are among the most mysterious objects in contemporary astronomy. Until relatively recently, their very existence was a matter of debate. Can planets exist without a star? And if so, how many are there in the universe? The answers obtained over the last 2 decades have proven to be both exciting and somewhat unsettling. Orphan planets not only exist, they may outnumber stars in our galaxy by some estimates, significantly more, perhaps by several times. This indicates that the dark interstellar space, which we have come to consider empty, is actually populated by countless cold, dark, invisible worlds drifting in the darkness without any source of heat or light. How do planets become orphans? There are several mechanisms, and each one is dramatic in its own way. The most common? Gravitational interactions within a young planetary system. In the early history of the system, when the planets have just formed and their orbits are not yet stable, gravitational interactions between the planets can cause one of them to gain enough momentum to leave the system forever. This is not a gradual process. It can happen relatively quickly, as a result of a series of gravitational maneuvers when a planet comes close to another planet or to the star itself, gaining additional speed sufficient to overcome the gravitational pull of the system. Models of planetary system formation show that such ejections can be quite common. A young version of our own solar system may have ejected several planets in its early history, which explains the current orbital configuration of the outer planets. The second mechanism involves a planet forming directly in interstellar space, following the same process as star formation, but from a cloud of material not massive enough to ignite nuclear fusion at its center. Such an object is a planet by mass, but a star by origin. It has never been part of any system and has always existed on its own. The boundary between such objects and brown dwarfs, failed stars, is a subject of ongoing debate in astrophysics. The specific object we are discussing in this chapter, Let's refer to it as CFB DSIR 2457 plus 2450, discovered in 2012 by an international group of astronomers, is located about 100 light-years from Earth and is one of the closest confirmed free-floating objects of planetary mass to us. Its mass is estimated to be roughly 4 to 7 times that of Jupiter, enough to be considered a planet, but not enough to ignite nuclear fusion and become a star. It does not orbit any star, it simply moves through interstellar space at a speed of several tens of kilometers per second, fast by human standards, but slow by galactic standards, going nowhere specific, without a destination, without a schedule, and without anyone waiting for its arrival. The surface temperature of CFB-DSIR is around 400 degrees Celsius. This is hotter than one might expect from a starless object, but the residual heat from the formation of the planet dissipates slowly, and over several hundred million years, the object has not yet completely cooled down. However, 400 degrees is already very cold compared to what it was in its youth, and the cooling process continues. In billions of years, the temperature will drop to a few tens of degrees above absolute zero, and this will be the final state of all orphan planets that do not receive external energy. Absolute zero, minus 273 degrees Celsius, is the theoretical minimum temperature that no object ever reaches in reality, but to which orphan planets unceasingly approach over geological epochs. The atmosphere of CFB-DSIR and similar objects is a story worth telling. At 400 degrees, clouds made of iron and silicates, the same materials that make up rocks, can exist in the atmosphere. As the temperature drops, other substances start to condense in the atmosphere: magnesium sulfide, sodium chloride, water ice. The atmosphere slowly changes its composition as the planet cools down. Some clouds disappear while others appear. This resembles a very slow, billions of years long change of seasons, only without the sun that would cause these changes, just internal heat, slowly dwindling like the embers in a fireplace that no one adds fuel to. Darkness, that is what primarily defines the world of an orphaned planet. Not just the darkness of night when stars are in the sky, not the darkness of a cloudy day. It is the absolute, crystalline, primordial darkness of interstellar space, interrupted only by the faint light of distant stars, so faint that it offers no warmth and no guidance, merely reminding one of the existence of the rest of the universe, indifferent and remote. The sky over a rogue planet is not the sky with a sun or moon. It is a deep black dome, sprinkled with stars just like any section of interstellar space, beautiful, solemn, and completely useless in terms of heating or lighting. There is something almost meditative in this concept, a world without dawn, without dusk, without changing seasons, without tides, and devoid of any external rhythm. Only slow, relentless cooling. Only darkness, which has always existed and will always exist. Some planetary scientists, when discussing rogue planets, use the word tranquility, not in the sense of cozy peace, but in the sense of the final, irreversible calming of all processes. This word is precise. A rogue planet is moving toward thermal death, a state where its surface temperature can no longer be distinguished from the temperature of the surrounding space, and no processes requiring a temperature differential can occur anymore. Could there have been anything resembling life on rogue planets? This question sounds almost provocative, but it is taken seriously in astrobiological literature. The argument goes like this: if a rogue planet is massive enough and retains residual heat from its formation over billions of years, there could theoretically be liquid oceans beneath its surface. Heat from radioactive decay of elements in its depths, combined with the residual heat from formation, could maintain liquid water at depths of tens or hundreds of kilometers beneath the icy surface, similar to what occurs on Europa or Enceladus. Without sunlight, photosynthesis is impossible, but chemosynthesis, the acquisition of energy from chemical reactions, is a viable alternative. There are entire ecosystems in Earth's oceanic hydrothermal vents that have never seen sunlight. This is, of course, an extraordinarily optimistic scenario that requires many factors to align. But the mere fact that scientists consider it speaks volumes. Life, once it has emerged, may be more resilient than we think, and it is worth searching for it even in the most unexpected places, even on a dark, cold, lonely object drifting between the stars without an address or schedule. The James Webb Space Telescope, launched at the end of 2021, has opened a new era in studying rogue planets. Its infrared sensitivity allows it to detect cold objects that are virtually invisible to optical telescopes, and already in its early years of operation, Webb has identified dozens of candidates for freely floating planetary objects in various star clusters. One of the most exciting discoveries was made in the Orion Nebula. Webb found around 100 pairs of rogue objects with planetary mass that orbit each other, not around a star, but around a common center of mass. These objects, informally dubbed Jupiter twins, represent an entirely new class of astronomical objects that do not fit into existing classifications. Two planet-sized objects bound by gravity, traveling together through interstellar space, without a star, without a system, only with each other. It's almost touching. Almost. Gravitational microlensing, a method of detecting orphan planets, has allowed us to estimate their total number in the galaxy. When a massive object passes between an observer and a distant star, its gravity acts like a lens, amplifying and distorting the light from that star for a short period. Analyzing the frequency of such events statistically estimates the number of objects causing the lensing, and results from several independent groups suggest that the galaxy may harbor anywhere from several hundred billion to several trillion free-floating objects of planetary mass. This number is difficult to comprehend. Trillions of dark, cold, lonely worlds drifting in the darkness between the stars, unknown, undetected, unnamed. The universe is more populated than we thought, but most of its inhabitants are objects best left untouched. If you want to truly grasp the existential scale of the orphan planet concept, step outside at night into an open field, far from city lights, lie on your back, and gaze at the sky. The stars above you are beautiful, numerous, and comforting. Now imagine that our sun is not among them. That all those points are equally distant and equally useless as sources of warmth. That the temperature is slowly dropping, not because night is falling, but because the night never ended and never will. This is life on an orphan planet. Or rather, this is the absence of life on an orphan planet. The difference is slight but significant. But if the darkness and cold of interstellar space seem too dull a threat, too slow, too abstract, then our next world offers something much more immediate. The next planet is located in our own galaxy, in a system visible to the naked eye, and it kills quickly, decisively, and with the chemical sophistication that makes its atmosphere a true masterpiece of toxicology. Welcome to WASP-79b, a planet where iron rains from the sky. Story 9. WASP-76b, a planet where iron falls from the sky. There is a recipe for the perfect cocktail of horror mixed only by the most reckless bartenders of the universe. Take a gas giant, place it several times closer to its star than Mercury is to our sun. Add tidal locking, so one side always faces the star while the other constantly hides in shadow. Heat the day side to 2,400 degrees Celsius. Wait for the metals in the atmosphere to begin to evaporate. And then allow the winds to carry those metallic vapors to the night side, where they condense and fall as rain. Not water rain. Not sulfuric, like on Venus. Not silicate, like on HD 18973b. Iron. Literally, drips of molten iron falling from the clouds during the twilight of a planet where day ends and night begins. WASP-76b is a world crafted not by nature, but by some particularly inspired author of dark fantasy. Except, of course, that nature indeed created it, and executed it with its trademark impeccable precision. The WASP-76 system is located in the constellation of Pisces, about 630 light-years from Earth. Its parent star is a yellow-white dwarf, somewhat hotter and larger than our Sun, shining about 3 times brighter. The planet was discovered in 2016 using the transit method, the same approach that led to the discovery of most exoplanets in our catalog, and immediately drew attention from researchers due to its parameters. The orbital period of WASP-76b is about 1.8 Earth days. Less than 2 days, its complete revolution around the star. The distance from the star is approximately 8% of the distance from Earth to the Sun. This means that the planet receives a radiation flux from its star about 4,000 times greater than what Earth receives from the Sun. These numbers immediately place WASP-76b in the category of ultra-hot Jupiters, a subclass of hot Jupiters where temperatures are so high that the chemical processes in the atmosphere fundamentally differ from anything we observe in more temperate conditions. The key discovery about the iron rain was made in March 2020 by a group of astronomers led by David Ehrenreich from the University of Geneva, working with data from the espresso spectrograph on the Very Large Telescope of the European Southern Observatory in Chile. They observed the planet during its transit, when it passed in front of the star's disk, and analyzed the spectrum of starlight that passed tangent to the planet's atmosphere. The method of transmission spectroscopy, which we have already mentioned in relation to HD 18733b, was applied here with exceptional accuracy thanks to the capabilities of espresso, one of the most stable and sensitive spectrographs in the world. The results were thrilling. As the planet entered the transit, when the boundary between the day and night sides, the leading terminator, crossed in front of the star, lines of neutral iron absorption were clearly present in the spectrum. Iron in gaseous form existed in the planet's atmosphere at the terminator. However, as the planet exited the transit, when the opposite terminator, where day meets night, crossed in front of the star, the iron lines in the spectrum disappeared. They were gone. The iron that existed in the atmosphere on one edge of the planet was absent on the other. The only reasonable explanation for this asymmetry is that iron condenses at the night terminator and precipitates down in the form of rainfall, falling as molten iron rain before it can move to the illuminated side. The physics of this process is elegant in its brutality. On the day side of WASP-76b, the temperature reaches 2,400 degrees Celsius. At this temperature, iron does not just melt, it evaporates. The boiling point of iron at normal pressure is around 2,860 degrees. Under the high-pressure conditions of the atmosphere on hot Jupiter, this temperature is slightly higher, but the difference is not significant. On the day side of WASP-76b, iron exists either in a gaseous state or right at the point of evaporation. Along with iron in gaseous form, there are other metals with high boiling points: nickel, chromium, magnesium, calcium. The atmosphere of the day side is a hot metallic mixture, with metal vapors mingling with molecules and atoms of hydrogen, helium, and other elements. Powerful winds carry this metal-laden atmosphere from the day side to the night side. The speed of these winds is around 18,000 kilometers per hour, which is approximately 5 kilometers per second. This is about 15 times faster than the speed of sound in Earth's atmosphere. The atmospheric flow carries iron vapors across the terminator, the boundary between eternal day and eternal night. And on the night side, the temperature drops to around 1,500 degrees. This is enough for iron to condense. Iron vapors begin to first transform into tiny droplets of liquid iron, then into larger ones, which fall down under the force of gravity. This is what we call an iron rain. It occurs in the terminator zone and on the night side, where the temperature is low enough for the condensation of metal vapors, but still high enough for iron droplets to remain liquid during their fall. It should be noted that the term low, when referring to 1,500 degrees Celsius, is one of the most striking examples of how extreme conditions change the frame of reference. 1,500 degrees is a temperature at which steel would have long melted, most ceramic materials would have lost their strength, and basalt would have turned into a liquid state. On WASP-76b, this is considered the cool night side, moderately enough for iron to condense. The atmosphere of WASP-76b is not just iron rain. It is a complex, multi-layered chemical system in which processes occur that have no analogs in the solar system. In addition to iron, spectroscopic observations have detected the presence of ionized calcium, neutral sodium, ionized barium, and several other elements in gaseous states in the planet's atmosphere. Barium is particularly intriguing. It was discovered in 2022 by a group of astronomers from the Canary Islands Institute of Astrophysics. Barium is one of the heaviest elements ever found in the atmosphere of an exoplanet, and its presence in the upper layers of the atmosphere of WASP-76b raises the question for scientists. What mechanism keeps such a heavy element high in the atmosphere, preventing it from settling down? The answer is apparently connected to intense vertical flows in the atmosphere, powerful updrafts that continuously mix atmospheric layers and lift heavy elements upward, counteracting gravitational settling. Further observations made using the James Webb Space Telescope after its launch have added new details to the portrait of the planet. Infrared observations have enabled the measurement of temperature distribution across the planet's disk with unprecedented accuracy and confirmed that the temperature difference between the day and night sides is around 1,000 degrees, sufficient for the described mechanism of condensation and evaporation of metals. The observations have also hinted at the presence of water vapor and carbon dioxide in the atmosphere, which is somewhat surprising given the extreme temperatures, but can be explained. Those molecules can exist on the night side and in deeper, less heated layers of the atmosphere. A hypothetical expedition to WASP-76b represents an exercise in gradually realizing more and more reasons to avoid such a journey. Let's start with the fact that 630 light-years is a distance that, with current technology, is insurmountable within a human lifetime, or even a civilization's existence. But let's assume that the technology has been resolved. You're approaching the system. Even at several million kilometers from the planet, your sensors detect intense hard radiation from the star. WASP-76 is an active star with regular flares, adding supplementary doses of X-rays and ultraviolet to the overall radiation background. You enter orbit. The thermal radiation from the planet is recorded by thermal sensors. It glows in the infrared range, heated and pulsating. On the day side, the sky shines with the dazzling orange-white light of the star, which occupies a significant portion of the celestial sphere because the planet is so close to it. You look at the terminator, the boundary between day and night. There, in the twilight strip, clouds are visible in the sky. Dark, heavy, metallic clouds. And something is falling from them, shimmering in the light of the star. Droplets of molten iron, ranging from a few microns to several millimeters, are plummeting down through the atmosphere. It is beautiful, much like the view from an airplane window at a storm front when you know you are safe. In orbit around WASP-76b, you are not safe. But that is another issue. An attempt to descend into the atmosphere would end in a collision with winds moving at 18,000 kilometers per hour and a rain of iron, which in this context is not a poetic metaphor, but a literal description of what would hit the spacecraft's hull. Molten iron droplets at such wind speeds move horizontally as much as vertically, just as we have already seen with HD 18733b and its glass rain. Temperatures of 1,500 degrees on the night side would melt most heat-resistant materials within minutes. Attempting to move towards the daylight side is even worse, 2,400 degrees and evaporating iron gas in the atmosphere. In this case, the chances of survival are non-existent in any direction, making WASP-76b a rare example of a planet that kills with equal efficiency no matter where you try to escape. The study of WASP-76b is one of the triumphs of modern exoplanet science, precisely because it shows that we can study the atmospheres of worlds we can never physically reach, uncovering phenomena that have no analogues in our solar system. The iron rain was not predicted prior to its discovery. It became a surprise, the result of observations that forced theorists to revise and expand the models of hot Jupiter atmospheres. This serves as a reminder that the universe is always richer than the most elaborate models we build to describe it, and that the best way to learn something new is simply to look more closely. WASP-76b is better understood in terms of its spectrum, a beautiful set of dark lines against a rainbow backdrop, where each line represents a signature of iron, calcium, sodium, or barium left in the light passing through the planet's atmosphere. It is abstract, it is distant, it is completely safe. This level of distance and abstraction is optimal for interacting with a planet where iron rain falls. From the metallic precipitation of the hot Jupiter, we move to a world of a different kind of danger. Our next planet on this tour kills not with heat or cold, nor with pressure or radiation, It kills by virtue of its existence next to an object that is one of the most destructive phenomena in the known universe. Our next destination is a system around a black hole. Welcome to the event horizon, a point of no return for light, matter, and careless interstellar tourists. Chapter 10: HMXBs and Planets Around Black Holes, the horizon beyond which there is nothing. There is a scene in the film Event Horizon, the one from 1997, where Sam Neill plays a scientist who creates a ship with an engine that uses an artificial black hole for jumps through space. The ship heads to Neptune, disappears, returns, and those who meet it quickly realize it has been to a place not just in a different part of space, it has been to somewhere fundamentally different, where the laws of physics do not behave normally, where space itself is a hostile environment. Director Paul Anderson made a horror film disguised as science fiction, and in this, he was more honest than most of his peers. The vicinity of a black hole is precisely where horror ceases to be a metaphor and becomes a physical constant. A black hole is not a hole. This is an important clarification because the word hole implies emptiness, a lack, a void in nothingness. A black hole is the complete opposite of emptiness. It is an object with colossal mass concentrated in an infinitesimally small volume, a mathematical point that physicists call a singularity. The singularity is surrounded by the event horizon, a sphere within which the second cosmic velocity exceeds the speed of light. This means that anything crossing the event horizon, matter, radiation, information, cannot return, as it would need to move faster than light, which is forbidden by the theory of relativity. The event horizon is not a physical surface, not a wall, not a barrier that can be felt upon crossing. It is simply a mathematically defined boundary. Upon crossing it, you won't feel anything unusual, provided the black hole is large enough for tidal forces at the horizon to be tolerable. At some moment, you will realize that there is no turning back. This moment will be the last when understanding anything at all makes sense to you. Planets in the vicinity of black holes are the subject of theoretical discussions and a few observational hints, but not confirmed discoveries in the same way that other planets in our guidebook are confirmed. Nonetheless, physics does not prohibit the existence of planets around black holes. On the contrary, it allows for several scenarios of their formation. The most likely scenario is that planets form from the accretion disk, that very rotating structure of gas and dust surrounding a black hole that slowly spirals into it. Accretion disk can be rich enough in solid material for planet-sized bodies to form from them, much like the mechanism by which planets form from a protoplanetary disk around a typical star. If such a planet's orbit is far enough from the event horizon, it may exist stably for billions of years. The system we are using as a reference for this chapter is a class of binary systems known as high-mass X-ray binaries, or HMXBs. In such systems, a black hole orbits a massive star, or the star orbits the black hole depending on your perspective, and actively absorbs matter from the star through the accretion disk. A famous example is Cygnus X1, the first astrophysical object for which it was reliably established that it is a black hole. Cygnus X1 is located about 6,000 light-years from Earth in the constellation Cygnus and is a black hole with a mass of about 21 solar masses, orbiting a blue supergiant. This system emits an incredibly powerful X-ray radiation, so powerful that it was discovered in the early 1970s using the first orbital X-ray telescopes. Theoretically, if there are planets in the Cygnus X1 system on wide orbits, far enough from the black hole and the blue supergiant, they would experience conditions that can be described as follows. The O-type blue supergiant, which is the companion to the black hole, emits several 100,000 times more light and heat than our Sun. Its ultraviolet radiation is capable of ionizing the atmospheres of planets at distances of tens of astronomical units. The X-ray radiation from the accretion disk, and even harsher and more penetrating radiation, adds doses that can sterilize planetary surfaces at distances of hundreds of astronomical units. Particles accelerated in relativistic jets, narrow streams of matter ejected along the axis of rotation of a black hole at near-light speeds, carry energies at which the concept of radiation protection, becomes engineering science fiction. Relativistic jets deserve separate mention because they are among the most powerful phenomena in the observable universe, and yet they remain insufficiently understood. When matter falls toward a black hole through the accretion disk, a portion of it is not absorbed but ejected perpendicularly to the plane of the disk in the form of two narrow beams, jets. The mechanism of jet formation is not fully understood, but is presumed to be related to the interaction between the rotating black hole and the magnetic fields of the accretion disk. Jets can extend for thousands and even millions of light years. Some jets from active galactic nuclei are visible on scales comparable to the sizes of galaxies. Matter in the jets moves at a speed that is a significant fraction of the speed of light, and carries such energy that when it interacts with the interstellar medium, it creates shock waves capable of heating gas to millions of degrees. A planet accidentally caught in the path of a jet would experience an effect that is difficult to describe in terms applicable to familiar phenomena. This is not radiation in the conventional sense. It is a stream of particles, each carrying energy comparable to that of alpha particles from radioactive decay, multiplied by the Lorentz contraction gamma factor. This is not a stream that can be shielded by lead sheets or a planetary-scale magnetic field. Any matter encountering the jet would be immediately ionized, heated, and likely gradually stripped away by a stellar wind, intensified by relativistic effects. A planet in a jet is a planet without a future. Fortunately, jets are very narrow and directionally focused structures, and the probability of being precisely in their path is relatively low, though for a specific planet in an unfortunate position, this solace is purely statistical. Gravitational effects near a black hole add an element to the overall picture that goes beyond simple physical danger and touches upon the very nature of space and time. General relativity predicts that near massive objects, time flows more slowly, an effect known as gravitational time dilation. For a black hole, this effect reaches extreme values. Near the event horizon, time for an external observer slows down infinitely, and the horizon itself is never reached, at least from the perspective of an outside observer. For an object falling into a black hole, the picture is different. It crosses the horizon in a finite proper time and continues its fall toward the singularity, while the external observer sees it forever frozen at the horizon. In the film Interstellar, the effect of gravitational time dilation was used as a key plot element. The characters descend onto a planet near the black hole Gargantua and discover that 1 hour on the surface corresponds to 7 years for those waiting on the ship. This is not a Hollywood invention. It is a real physical effect, but in the film, a black hole with a mass of 100 million solar masses was required to achieve it. Real stellar black holes, like the one in Cygnus X1, are much less massive, and noticeable gravitational time dilation would require getting significantly closer to the event horizon than is compatible with survival in any other form. Tidal forces near black holes are another factor that turns any approach to them into a definitively fatal endeavor. Tidal forces are the difference in gravitational acceleration between the near and far sides of an object. For stellar black holes, with masses of several tens of solar masses, tidal forces at the event horizon are immense. The difference in gravitational acceleration between the head and feet of a person approaching the horizon would amount to billions of accelerations due to gravity. Astrophysicists refer to this phenomenon as spaghettification. The object is literally stretched into an infinitely thin thread as it approaches the singularity. For more massive black holes, supermassive ones with billions of solar masses, the tidal forces at the horizon are weaker, which paradoxically means that a person could cross the event horizon of a supermassive black hole without feeling any immediate discomfort. This is perhaps the subtlest kind of trap of all, crossing the point of no return without realizing it, only to understand what has happened when the tidal forces begin to increase as one moves toward the singularity, and it will already be impossible to retreat. What would happen if a planet existed on a stable orbit in a system with a stellar black hole, far enough not to be immediately destroyed, but close enough to feel its influence? The X-ray radiation from the accretion disk would sterilize the surface. Relativistic particles from the jets, if the orbit falls within their cone, would create an additional background radiation. Tidal deformations, significantly less than on Io but still noticeable, would heat the planet's interior. gravitational time dilation on such an orbit would be small, but real. It would be a world with a constant X-ray sky, where instead of a sun, the accretion disk would glow in the sky, shifting from pale blue at the outer edge to intensely white at the inner edge, with a dark point at the center representing the event horizon, a point that you cannot see directly but can determine by how light bends around it, creating characteristic gravitational rings. Beautiful. Completely deadly. Just like everything else in this guide, the vicinity of a black hole is best observed through images from X-ray telescopes, beautiful false colors translating invisible X-ray radiation into the visible spectrum, swirling accretion disks, nebulas heated by jets. It looks beautiful from a distance of thousands of light years. From a distance of thousands of kilometers, this is the last thing you see. The difference in perception is substantial. From black holes, the darkest objects in the universe, we move to a world where the danger lies not in a lack of light, but in its absolute excess. The next planet in our guide exists in a system where its star periodically produces flares so powerful that they can blow away the planet's atmosphere in a geologically insignificant amount of time. This is a world around a red dwarf, the most common type of star in our galaxy and, as it turns out, one of the most unreliable neighbors. Welcome to Proxima b, a planet around the closest star to us, which would very much like to become our second home. It would very much like to. Story 11. Proxima Centauri b, the nearest neighbor that cannot be trusted. There is a particular charm in the concept of a closest neighbor. In human experience, a neighbor is someone nearby who can help in case of need, someone you can knock on the door of. Neighborliness implies some form of relationship, reciprocity, at least minimal availability. When in 2016, the European Southern Observatory announced the discovery of a planet orbiting Proxima Centauri, the closest star to the Sun, located just 4.2 light-years away, global media immediately exploded with headlines about a second Earth and the closest candidate for the existence of life. The planet is located in the so-called habitable zone of its star, at a distance where the existence of liquid water on its surface is theoretically possible. It is about Earth-sized. It orbits its star. All of this sounded like the beginning of a very good story. The problem is that the star around which Proxima b orbits is one of the most temperamental and unpredictable objects in our galactic neighborhood. And this temperament has very specific physical consequences for any planet unfortunate enough to be nearby. Proxima Centauri is a red dwarf of class M, the most common type of star in our galaxy. About 70% of all stars in the Milky Way are red dwarfs, making the question of their suitability for hosting planets one of the central issues in astrobiology. Red dwarfs are small. Proxima Centauri has a mass of about 1/8 of the Sun, and a radius of about 1/7 of the Sun. They are cold by stellar standards. Proxima's surface temperature is around 3,100 degrees Celsius, compared to 5,500 of the Sun. They are dim. Proxima's luminosity is about 1/600th of the Sun's, and they are extraordinarily long-lived. If our Sun will shine for about 10 billion years, Proxima Centauri will burn for another 4 trillion years, 400 times longer than the current age of the universe. In terms of long-term stability, this sounds excellent. The problem is that Proxima Centauri is a flaring star. This means that it regularly produces powerful flares, sudden bursts of energy from the surface caused by the restructuring of magnetic fields. There are flares on the Sun as well, and they can lead to geomagnetic storms, disrupt radio communications, and, in rare cases, disable satellites. X-class solar flares, which are the strongest type, occur several times a year during solar maximum and are significant enough for astronomers to monitor them closely. Flares on Proxima Centauri occur much more frequently and are substantially more powerful relative to the star's brightness. In March of 2017, a flare on Proxima was recorded that increased the brightness of the star by about 10 times in just a few dozen seconds, an event that, in relation to our Sun, would mean something utterly catastrophic for the entire solar system. And this was not an exceptional, rare flare. It was one of many that happen regularly on Proxima. Why are red dwarfs so volatile? The answer lies in their internal structure. Unlike the Sun, which has a radiative zone, a region where energy is transported by radiation, and a convective zone only in the outer layer, red dwarfs are fully convective objects. This means that convection, mixing of material, occurs throughout the entire volume of the star, from the core to the surface. Full convection creates very intense and tangled magnetic fields, and it is the restructuring of these fields that causes flares. A red dwarf is not a quiet, calm star that burns steadily for billions of years. It is a restless, constantly bubbling object whose magnetic fields are continuously intertwined, accumulating energy and periodically releasing it explosively. For Proxima b, the proximity to its star, which is necessary for it to be in the habitable zone, is a source of particular vulnerability. The habitable zone of a red dwarf is located much closer to the star than the habitable zone of the Sun, simply because the star is dimmer, and to receive the necessary amount of heat, it needs to be closer. The orbital period of Proxima b is about 11.2 Earth days. For comparison, Mercury orbits the Sun in 88 days. Proxima b orbits its star roughly 8 times faster than Mercury, and it does so while being in the habitable zone. This closeness to the source of flares creates a fundamental problem. The distance needed to receive sufficient heat is also the distance at which the star's flares hit the planet with maximum intensity. Ultraviolet and X-ray radiation during Proxima's flares reaches Proxima b in amounts capable of destroying the ozone layer, if it has even had time to form. Ozone is depleted by specific wavelengths of ultraviolet radiation, and a powerful stellar flare can destroy a significant portion of a planet's ozone layer in just a few hours. Recovery of the ozone layer after a major flare takes years. If solar flares occur more frequently than once every few years, and they do on Proxima b, the ozone layer does not have time to recover between events and gradually becomes depleted. Without the ozone layer, ultraviolet radiation reaches the surface in amounts that are destructive to most known forms of life. This does not mean that life is impossible. Some organisms are resistant to high doses of ultraviolet light, but it does mean that conditions on the surface of Proxima b are significantly harsher than on Earth. Another issue is the stellar wind of Proxima Centauri, which may prove to be more serious than the flares. Stellar wind is a constant stream of charged particles emitted by a star. Our Sun has a relatively moderate stellar wind, and Earth's magnetic field effectively deflects much of it, creating a magnetosphere, a protective bubble around the planet. However, Proxima Centauri's stellar wind is significantly more intense relative to the star's size. Estimates suggest it is thousands of times stronger than solar wind when considering the distance to the habitable zone. This means that the pressure from the stellar wind on the atmosphere of Proxima b is thousands of times greater than that of the solar wind on Earth's atmosphere. If Proxima b does not have a sufficiently strong magnetic field, which is a significant question since the presence and intensity of a magnetic field depend on the planet's geological activity and composition, the stellar wind from Proxima could gradually strip away the planet's atmosphere into open space. This process is known as atmospheric blow-off, which has already occurred with Mars. When Mars lost its global magnetic field around 4 billion years ago, its atmosphere was gradually blown away by solar wind to its current state, with a pressure of less than 1% of Earth's. On Proxima b, this process could occur significantly faster due to the vastly more intense stellar wind. If the planet initially had an atmosphere, and it almost certainly did if it formed as a rocky body, the question remains how much of that atmosphere has survived after billions of years under the stellar wind from Proxima. Tidal locking is the next issue, and it is particularly problematic because it is a direct consequence of the only advantage Proxima b has, its proximity to a warm star. With such a short orbital period and such a small distance from the star, the gravitational tidal forces from Proxima have likely long ago led to tidal locking of the planet. It is always facing the star on one side, just as the Moon does with Earth. This means there is eternal day on one side and eternal night on the other. The daytime side is scorched and irradiated. The nighttime side is frozen, possibly reaching temperatures hundreds of degrees below zero. The terminator, the strip of perpetual twilight between them, is the only area where temperatures are theoretically compatible with liquid water. The atmosphere under tidal locking behaves unpredictably. If it has sufficient density, it can redistribute heat between the day and night sides, softening the extremes. This is the scenario considered to be the most optimistic for Proxima b. If the atmosphere is thin or even non-existent, the day side turns into a scorched desert, while the night side becomes a frozen hell, with no middle ground. Computer models of atmospheric circulation on Proxima b yield a wide range of results depending on initial assumptions about the composition and density of the atmosphere, from relatively mild conditions at the terminator to complete atmospheric collapse on the night side, where gases freeze and fall to the surface as ice. The uncertainty here is immense, and this uncertainty itself characterizes the planet. We do not know enough to be confident about anything other than the fact that conditions there are significantly more complicated than one would hope. What do we know for certain about Proxima b? We know its orbital period, 11.2 Earth days. We know that its minimum mass is about 1.7 Earth masses. This is the lower limit, and the actual mass could be higher. We know that it lies within the habitable zone of Proxima, and we know that observing it directly with current technology is nearly impossible. It is too small and too close to the star to be resolved in an image with existing tools. Everything else, the composition, the presence of an atmosphere, the existence of water, geological activity, remains in the realm of speculation and models. It is astounding for the closest exoplanet to us. We know more about some objects thousands of light years away than about a planet orbiting our nearest star. In 2016, the Russian billionaire Yuri Milner and physicist Stephen Hawking announced the Breakthrough Starshot Initiative, a project to send miniature spacecraft accelerated by laser pressure to the Alpha Centauri system, the triple star system that includes Proxima, at speeds of around 20% of the speed of light. At this speed, the journey would take about 20 years. Conceptually, the project is captivating. Tiny sailboats carrying a minimal set of sensors and cameras passing through the Proxima system and sending data back. At 20% of the speed of light, the data would take another 4 years to return to Earth. In total, from launch to receiving the first images, around 25 years. The technical challenges of the project are immense. Creating a craft light enough to be accelerated by a laser and strong enough to survive an interstellar journey is an engineering challenge far beyond current capabilities. But the very formulation of the task indicates that humanity is seriously considering the exploration of Proxima, if only for a quick flyby. Proxima b entices precisely because of its proximity and potential. It is a planet that could be a second Earth, if only its star were a bit calmer, if it had a sufficiently strong magnetic field, if the atmosphere could be preserved, if water could exist in liquid form, if. The list of conditions needed for Proxima b to be suitable for life is longer than one would hope. And the star, this restless, flaring red dwarf, is the main argument against it. It is too close, it is too active. It often reminds us that proximity brings not only warmth, but everything else that a star can offer its planet. And it can offer a lot of things, most of which can be deadly. Proxima b is better contemplated as an idea, a reminder that the closest exoplanet has already been found, yet it disappoints precisely because it was so close to hope. 4.2 light-years may seem like a short distance in cosmic terms, yet it feels like infinity with our current technology. It separates us from a world that could have been beautiful but turns out to be problematic. Perhaps this is the main lesson of our guide. The universe is generous with beautiful views, but miserly with hospitality. From a star that is too active, we move to a world that kills in a completely different way, not through radiation or flares, but through pure, absolute, primordial gravitational force. The next planet on our list exists around an object that pulls in space itself, and does so with such intensity that the concept of a safe orbit requires the most careful mathematical analysis. Our next world is a planet in a binary system with a neutron star, where the very notion of a stable orbit is subjected to ongoing gravitational negotiations among bodies with vastly different ideas about where the planet should reside. Chapter 12. A planet in a binary system with a neutron star, dancing on the edge of ruin. There is a special kind of ballet that mathematicians call the three-body problem. When two massive objects orbit each other, their gravitational fields create a complex but predictable landscape, a system of equilibrium points and orbital resonances where a third body may exist stably or unstably, depending on the initial conditions. The Chinese writer Liu Cixin dedicated an entire trilogy to this problem, the three-body problem, depicting a civilization inhabiting a system of three stars where orbital chaos renders any long-term planning futile and the very concept of a normal climate becomes an unattainable luxury. A planet in a binary system with a neutron star represents something fundamentally worse than a system of three ordinary stars. Here, it is not simply three bodies of different masses. Here is an object that is a concentrated anomaly of physics, packed into 20 kilometers in diameter, orbiting a normal star, while a planet tries to maintain a stable orbit amidst this gravitational circus. This is not ballet. This is rodeo. And the planet is always in the role of the bull. The system we are considering in this chapter, binary systems like PSRB 1960 plus 10, known as systems with a neutron star and a companion star, represents one of the most dynamic and extreme classes of astrophysical objects. In such systems, a neutron star, the remnant of a supernova explosion, orbits a regular star, gradually pulling material from it through an accretion disk. This is a slow, methodical, and relentless process of absorption. The neutron star literally consumes its companion, accumulating mass and speeding up its rotation. Meanwhile, the companion gradually loses mass, its layers swelling and deforming under tidal forces, while the orbit of the system slowly evolves. For any planet in such a system, this means that conditions are never constant. They slowly but steadily change over the course of millions and billions of years. The neutron star itself is an object whose physical properties border on the limits of what we understand about matter. Its diameter is about 20 kilometers. Its mass ranges from 1.5 to 2 solar masses. This means that the density of matter in its core is about 800 million tons per cubic centimeter, a density at which ordinary atoms cannot exist. Electrons are pressed into protons, forming neutrons, and it is this neutron soup, neutron matter, that constitutes the core of the neutron star. At the center of the object, where pressure reaches its maximum, physicists theorize the existence of even more exotic states of matter, quark-gluon plasma, strange quark matter, or other forms that are theoretically predicted but experimentally unconfirmed. The neutron star acts as a laboratory for high-energy physics that we cannot replicate on Earth, yet it exists in the same system as our hypothetical planet. The magnetic field of the neutron star is among the strongest in the universe. The pulsar's magnetic field is trillions of times stronger than Earth's. For a planet in the same system, this means a constant exposure to a magnetic field of such intensity that it can influence charged particles in the atmosphere, creating currents and heating the ionosphere. However, the magnetic field is not the main threat. The primary threat is the instability of the orbit itself. In a binary system, the planet's orbit is constantly disturbed by the gravitational influence of both massive bodies. The neutron star and its companion rotate around a common center of mass, which itself moves in relation to the planet. The gravitational landscape of the system is in constant flux with the orbital period of the binary pair, sometimes increasing the planet's attraction to one body and sometimes to the other, creating periodic disturbances in its orbit. Depending on the ratio of the orbital periods, these disturbances can build up in resonance, and at that point, the planet's orbit slowly but surely degrades, becoming increasingly elliptical until eventually it comes too close to one of the bodies and is either consumed or ejected from the system. Computer simulations show that in most binary systems with a neutron star, stable planetary orbits exist only within narrow ranges of distances, islands of gravitational stability surrounded by zones of chaos. To find oneself in such a system means living on an island, surrounded on all sides by water that is gradually rising. The X-ray radiation of the system adds a physical threat to this picture from an additional dimension. When a neutron star actively accretes material from a companion star, the accretion disk heats up to millions of degrees and emits a powerful stream of X-rays. Such systems are called X-ray pulsars or X-ray binaries, and they are among the brightest sources of X-ray radiation in the galaxy. For a planet in the same system, this means an X-ray background thousands of times greater than what we observe near ordinary active stars. If X-ray flares for Proxima b are a periodic event, here it is a constant background, an integral part of the environment. Periodic X-ray flares are a separate category of events in X-ray binaries. When the accumulation of matter on the surface of a neutron star reaches a critical mass, a thermonuclear explosion occurs on its surface, an X-ray burst of the first kind. Within a few seconds, the brightness of the system in the X-ray range increases by tens to hundreds of times, then slowly fades over several minutes. This is not a theoretical phenomenon. X-ray binaries exhibiting such bursts have been observed in our galaxy and studied in detail. For a planet in the system, each such burst is a radiation event that far exceeds the largest solar flares. If flares from Proxima Centauri can destroy a planet's ozone layer in hours, a burst from a neutron star can sterilize a planet's surface in seconds, literally in the few seconds it takes for the system's brightness to peak. The history of observing X-ray binaries with neutron stars is a story in which each discovery adds a new layer of extremity. The Uhuru X-ray telescope, the first orbital X-ray telescope launched in 1970, discovered hundreds of X-ray sources in our galaxy, many of which were subsequently identified as X-ray binaries. Subsequent missions, Einstein, Rosat, Chandra, and XMM Newton, mapped these sources with increasing detail, unveiling ever-new types of X-ray binaries and increasingly exotic modes of their behavior. One of the most exciting discoveries has been the so-called magnetars, neutron stars with magnetic fields 1,000 times more powerful than those of ordinary pulsars, capable of producing gamma-ray bursts that can literally be seen billions of light-years away. If the neutron star in our system is a magnetar, which adds another level of extremity to all that has been said, one can only speak of the planet in the same system in the past tense. Does such a planet have any chance of retaining anything interesting on its surface? An atmosphere, water, geological activity? Theoretically, yes, this could be possible with a sufficiently distant orbit and a powerful enough magnetic field generated by the planet itself. The distance weakens the X-ray radiation proportionally to the square of the distance. That is, if you move 10 times farther away from the system, the intensity of the radiation decreases by 100 times. At a distance of several astronomical units from the X-ray binary, the levels of radiation might drop to values where a planetary atmosphere could provide adequate protection. However, at such distances, the planet might fall outside the gravitational stability zone of the system, or receive so little heat from both components that it becomes a frozen world. Finding the ideal balance where radiation is sufficiently low, the orbit is stable, and there is enough heat for liquid water is exceptionally challenging, if it even exists in such a system. Gravitational waves are the final stroke in the portrait of this world, and it's a particularly unique stroke. Binary systems with neutron stars are sources of gravitational waves, ripples in the fabric of spacetime, predicted by Einstein in 1916 and first directly detected by the LIGO detector in 2015. The binary neutron star PSRB 1913+16, discovered in 1974 by Halson Taylor, provided the first indirect evidence of the existence of gravitational waves. The orbital period of the system was slowly decreasing, exactly as predicted by the general theory of relativity for a system losing energy through the emission of gravitational waves. Halson Taylor received the Nobel Prize in Physics for this discovery in 1993. For a planet in a system with a neutron star and its companion, this means that the system itself is gradually approaching. The orbits of the two massive bodies are shrinking as the system loses energy through gravitational radiation. Eventually, in millions or billions of years, they will merge, producing a burst of gravitational waves and likely a short gamma-ray burst. For our hypothetical planet, this means a gradual transformation of the gravitational landscape of the system throughout its history. The planet's orbit evolves, conditions change, and the outcome is determined long before it occurs. A planet in a binary system with a neutron star is better perceived as a mathematical object, as a solution to a system of differential equations describing orbital dynamics in the field of two unequal masses. It is a beautiful solution, complex, unstable, requiring precise initial conditions for existence, and doomed to change with the slightest disturbance of those conditions. This is a world that exists not in defiance of physics, but in exact accordance with it, and that is why its existence is so fragile and so finite. We have reached the final stop of our guide, the 13th planet. The concluding chapter of our cosmography of death is perhaps the most philosophically unsettling of all. This is not a world that kills with heat or cold, pressure or radiation, gravity or darkness. This is a world that kills with the very scale of its existence, a planet near a quasar, the brightest and most powerful stable source of energy in our known universe. A planet illuminated not by a star, but by an entire ravenous monster at the center of the galaxy, consuming matter at a rate of several solar masses per year and converting it into radiation that is visible billions of light years away. Welcome to the quasar. Welcome to the last page of our guide. History 13, and last, the planet near the quasar, the end of the world in a literal sense. There comes a moment in some journeys when you realize you've gone further than planned, when the distance behind you is so great that turning back is almost as far as moving forward. When the landscape around you has become so alien that familiar landmarks have lost their meaning. This is the state an imaginary explorer finds themselves in as they reach the final point of our route, the surroundings of the quasar. Not just a star, not a neutron star, not a stellar mass black hole, but a supermassive black hole actively consuming matter and turning this process into the brightest stable phenomenon in the universe. This is the end of our guide, and it fulfills its place on the list just as precisely as the final chord of a symphony fits. Quasar is an abbreviation of quasi-stellar object, a name given to these sources in the 60s when astronomers first discovered them in the radio range and found that they looked like point sources similar to stars, but had redshifts indicating distances of billions of light years. An object shining like a star but visible from billions of light years away means its luminosity must exceed that of a star by an unimaginable amount. The first attempts to explain the nature of quasars were filled with exotic hypotheses, from giant explosions to new, unknown physical processes. Eventually, it turned out that the explanation was both simpler and scarier than any exotic theory. A quasar is the core of an active galaxy, at the center of which lies a supermassive black hole with a mass ranging from several million to several billion solar masses, actively consuming surrounding matter. The most famous and well-studied of the nearby quasars is 3C 273, located in the constellation Virgo at a distance of about 2,400,000,000 light-years. This means that the light we are currently receiving from it left that region when Earth did not yet exist in its current form, when multicellular life was just beginning its uncertain march across the planet. 3C 273 is the brightest quasar in the night sky. It can be seen in a small amateur telescope as a faint point of 13th magnitude, indistinguishable from ordinary stars unless you know that you're looking at an object whose luminosity exceeds that of our Sun by about 4 trillion times. 4 trillion. This is not a typo or a poetic exaggeration. One quasar emits as much energy as 4 trillion of our Sun simultaneously, and it does this over an area comparable to the size of the solar system, not over the area of an entire galaxy hundreds of thousands of light-years in diameter. The source of this energy is gravity, the same force we discussed in the context of neutron stars and black holes, but here it operates on scales that leave no room for mitigated phrasing. Matter falling into a supermassive black hole first forms an accretion disk, a rotating structure of hot gas and plasma that spirals toward the event horizon. In the process of this rotation, the matter rubs against itself, heating up to millions and even billions of degrees, and emits radiation across all wavelengths of the electromagnetic spectrum simultaneously. The efficiency of this mass-to-energy conversion process is about 10%. That is, 10% of the mass of the matter falling into the black hole is converted into pure energy. For comparison, in nuclear reactors on Earth, the efficiency is less than 1%, and in a hydrogen bomb, it's about 1%. A quasar is the most efficient engine in the universe, fueled by gravity and producing radiation so powerful that it is visible from billions of light-years away. Planets near quasars are objects whose existence is the subject of active theoretical research. For a long time, it was believed that planets could not form or survive in galaxies with active nuclei. The intense radiation from a quasar seemingly should destroy protoplanetary disks and hinder the accumulation of matter into planetary bodies. However, observations with the James Webb Space Telescope and other modern instruments have shown that even in galaxies with active nuclei, star formation and the formation of planetary systems continue, albeit under altered conditions. Planets in such galaxies are real. The only question is how they make it. The quasar QSOB 0538 plus 419 is one of the most studied in terms of possible planetary existence. Its surroundings contain stars with protoplanetary disks, and some of these disks show signs of ongoing planet formation, despite all this occurring thousands of light-years from the active galactic nucleus. But even thousands of light-years are not a safe distance from the quasar, and this is what makes such systems special in our catalog. The radiation of a quasar spans the entire electromagnetic spectrum simultaneously, from radio waves through infrared, visible light, ultraviolet, X-rays to hard gamma radiation. This is not a narrow beam like the jets of a neutron star. It is a spherical emission in all directions, although the quasar jets, which exist along the rotation axis of a black hole, pose an additional and specific threat. The intensity of this radiation decreases with distance, proportional to the square of the distance. However, given the initial power of the quasar, this decrease should be considered not in units of solar luminosity, but in units of galaxy luminosity. At a distance of several thousand light-years from the quasar, the intensity of ultraviolet radiation is hundreds of thousands of times greater than what Earth receives from the Sun. X-ray radiation at the same distance is millions of times more intense than the background on Earth. This is not an environment where the existence of an atmosphere is taken for granted. Quasar jets are a separate category of phenomena worthy of attention. Relativistic jets of active galactic nuclei are the most powerful continuous energy sources known in the observable universe. The jet of quasar 3C273 extends over a distance of about 150,000 light-years. This is 1.5 diameters of our galaxy. The material in the jet moves at a speed exceeding 99% of the speed of light, and at such speeds, relativistic effects become significant. The Lorentz gamma factor for these speeds means that particles in the jet carry energies for which ordinary concepts of radiation protection and shielding lose their physical meaning. A planet caught in the path of the jet would experience an impact comparable to a close supernova explosion, not instantaneously, but continuously, for thousands or millions of years, as long as the rotation axis of the black hole is directed towards it. The gravitational influence of a supermassive black hole in a quasar is felt at distances that are hard to imagine. The mass of the black hole at the center of a typical quasar ranges from several hundred million to several billion solar masses. The radius of the gravitational influence sphere of such an object, the zone in which the gravity of the black hole dominates over the gravity of the surrounding galaxy, ranges from several hundred to several thousand light-years. Stars within this sphere orbit the black hole similarly to how stars in ordinary galaxies orbit the galactic center, but at significantly higher speeds. The velocities of stars in close proximity to a supermassive black hole reach several percent of the speed of light. In our own galaxy, star S2, orbiting Sagittarius A star, our central black hole with a mass of about 4 million solar masses, moves at a speed of about 3% of the speed of light at its closest point in its orbit. For more massive black holes of quasars, the orbital speeds of objects are even higher. A planet in close proximity to a quasar exists in a gravitational field where tidal forces significantly exceed everything we have discussed in previous chapters. At a distance of several light-years from the quasar, the tidal forces of the supermassive black hole are comparable to the gravitational forces acting in binary star systems. They constantly deform the planet, heat its interior, and affect its orbit. Tidal capture at such distances is impossible. The orbital period would be too long. But the gradual evolution of the orbit under the influence of gravitational disturbances from other stars, from the accretion disk of the quasar itself, and from relativistic effects in the strong gravitational field is inevitable. A planet near a quasar is an object with a finite lifespan, measured not in years but in millions of years. Sooner or later, its orbit will evolve to a point of no return. The beauty of a quasar, and this beauty deserves separate mention, is one of the most grandiose in all of astronomy. Close to a quasar, the sky would appear as follows. In the center, a blindingly bright core, surrounded by a glowing accretion disk that transitions from dark red on the outer edge through orange, yellow, and white, to bluish-white in the innermost sections, where the material is heated to hundreds of millions of degrees. Jets shoot perpendicularly from the disk in both directions, two columns of plasma and light, visible as bright, almost straight beams stretching over thousands of light-years. The galaxy around it, a radiant, active entity infused with radiation from the core, does not serve as a dark backdrop. It glows itself, its stars ionized by intense quasar radiation, and its gaseous nebulae fluorescing in ultraviolet light. This is a sky that never darkens. This is light that never fades. This is beauty that kills, not metaphorically, but in the precise physical sense of the term. Is there life near quasars? This question sounds rhetorical, but it is seriously addressed in scientific literature, and the answer is not a definite no. Quasars do not exist forever. The active core of a galaxy becomes inactive when its accretion material is depleted. Our own galaxy has a supermassive black hole at its center, Sagittarius A star, which is currently mostly inactive but was apparently a quasar in the past. This means that the stars in our galaxy, including possibly our Sun, have gone through a period when the central core was significantly more active. If life arose on Earth despite this, perhaps the sufficient distance from the core provides protection. The distance from Earth to Sagittarius A star is about 26,000 light-years. This has evidently been enough. However, planets located a few thousand light-years from an active quasar core during its peak activity would have significantly less chance of maintaining anything that could be called a favorable environment. Quasar 3C 273 is best observed with a small telescope with an aperture of 150 millimeters on a dark, moonless night, as a faint point, almost indistinguishable from ordinary stars. He will be there, in the constellation of Virgo, 2,400,000,000 light-years away from you, shining with a brightness of 4 trillion suns, completely unaware of your existence. This is the safest form of interaction with a quasar, observing from a distance of over 2 billion light-years. We recommend not to shorten this distance. And now we have reached the end of our journey. 13 worlds, 13 ways in which the universe showcases its attitude toward uninvited guests. Venus with its acidic clouds and pressure of 92 atmospheres. Jupiter with its endless hurricanes and deadly radiation belts. Neptune with its supersonic winds at the edge of the known world. HD 189,733b with its horizontal rain of molten glass. Io with its relentless volcanoes and sulfur lakes. Kepler 70b, burning brighter than the sun. PSRB 157 plus 12 with its planets at the death beacon. An unnamed orphan planet drifting in eternal darkness. WASP 76b with its iron rain, the vicinity of a black hole from which there is no return. Proxima b, around a star that cannot be trusted. A planet in a double system with a neutron star, dancing at the edge of a rupture. And finally, a quasar where the very concept of safety is academic. What does all of this tell us about the universe? First of all, that it is extremely rich in phenomena, processes, and conditions that were unknown to several generations before us. Each of the described planets is not just a catalog of dangers, it is a window into physics that cannot be achieved in laboratory conditions. The pressure at the center of Jupiter, the surface temperature of Kepler 70b, the magnetic field of a neutron star, the luminosity of a quasar. All of this represents natural experiments that the universe continuously conducts, and our task is to observe them from a safe distance and extract knowledge. The second conclusion is more personal and more troubling. Earth is an exception, not the rule. Among thousands of known planetary systems, Among billions of possible worlds in our galaxy, among trillions of galaxies in the observable universe, our blue dot with its temperate climate, protective magnetic field, ozone layer, stable star, and gravity just right to retain an atmosphere without crushing bones, is a rarity bordering on incredulity. Not because life is impossible nowhere else, not because we are alone in the universe, but because the conditions under which life flourishes and develops to the point it can look through a telescope and question its own origins require the simultaneous alignment of many factors. Any of the 13 worlds we described could have been Earth, and none of them became it. The third conclusion is the most important and simplest. Step outside tonight. Look up. Find Venus. It is the brightest object at twilight. Find Jupiter. You can't mistake it for anything else. If you're lucky with the weather and the telescope, find that pale blue dot of Neptune. They are all there, in their places, busy with their eternal activities, their hurricanes, their volcanoes, their acid rains. They existed before you and will exist after. And here you stand on a planet that, despite all efforts of the universe to prove otherwise, has turned out to be surprisingly, incredibly, undeservedly suitable for life. This is not a reason for complacency. This is a reason for gratitude. And for caution, because the universe has not promised that this will last forever. It just isn't objecting for now. Your guide is closed. Welcome home.